Hello everyone. This series is going to be very special for you as it is one shot series. We are going to cover each and every important which will help you in this crash course. Here in the first lecture, I'll be beginning with regular expression and finite automata of theory of computation subject. You know, the theory of computation is very important, which will have the weightage around 8 to 9 marks in every year. So I feel you must learn. As I explain each and every concept through the questions, you will like a lot in this series. So let's begin what I'm going to cover in this series. The first topic, which is regular expression and finite automata. Once you complete this, you will have all the basic knowledge of the TOC so that you can understand what are the regular languages and non-regular languages in second video. Then the closure properties of regular languages, where you will be learning all the kinds of operations which are required to understand, like what is the union of two regular languages and intersection and so on. Then we will go for the second, you can think as the second part. As the first part, you will be covering with all the basics and all the important concepts. Maybe you will have half of the weightage of the TOC in this, the first three topics sometimes. Then we will have the grammars, where regular grammar and context-free grammar both are discussed. Then we have the push-down automata along with the various languages which are context-free languages and also deterministic context-free languages. Here we'll be learning how to identify CFLs and DCFLs. Then we have the sixth video, closure properties of CFLs and DCFLs. Okay. Then finally, the Turing machine and undecidability. If you look at the weightage of this theory of computation, then the two topics will have at least 2 to 3 marks, and the last topic you will be having around 2 marks, and then remaining marks will lie somewhere in this. And closure properties are very important. Here closure properties of regular languages and closure properties of CFLs and DCFLs, and one more closure properties I'll be covering in Turing machine, which is for recursive languages and recursively enumerable languages. Let's begin with the first topic, regular expressions and finite automata. Do you think that I can begin with this regular expression and finite automata directly? No. So we'll have some basics before starting regular expressions and finite automata. Then we will move to regular expressions. Okay. This is what I want to explain as basics in theory of computation, where first you should know what is a string and how do you form a string for the given over the given alphabet, and what are the various operations can be applied over the strings, and also what is language and what are the operations you can apply over the language. Also, you know that language is called as a set, right? The set synonym is here in TOC is a language. And then we will look at how this TOC is combined with various formal languages with the help of Chomsky hierarchy. So let's start with the first very simple and basic to the theory of computation, that is, what is a string? Okay. Yeah. So what do you need? If you want to form a string, what do you need? That is alphabet. So first thing is you require alphabet, that you may denote with sigma, where alphabet could be any set of symbols, like you may use 0 or 1, or sometimes you may use A, comma B. It need not be binary alphabet, it could be even unary alphabet. Unary alphabet in the sense it has only one symbol that is used to define the string or language. Or you may use ternary alphabet like 0, 1, 2, or you may use X, Y, Z. It need not be digits or alphabet letters. You may also use like symbols, depends on your requirement. Likewise, every alphabet is set of symbols, but how many symbols you can keep? Finite number of symbols. If you want to know what is alphabet, it is set of finite number of symbols. It must be defined before writing any string. So first you should read what is alphabet is given in the problem. Problem to problem, it may vary. So first you read what is an alphabet. Using this alphabet, how you are going to form the strings of a language. So I understood the alphabet is nothing but set of symbols, which must be finite number of symbols. As you know, if the set is infinite, it is impossible to learn the alphabet itself. So that is reason you require, like you go for English alphabet or Hindi alphabet or any language you take in the world, the alphabet always contain finite number of symbols. Okay, so I believe what is alphabet, everybody understood. Now let's move to what is a string. Okay, what is a string? String is a sequence. What is it? It is a sequence of the symbols. Where do you get the symbols? Defined over the sigma. So these symbols are defined over sigma. Whatever the sigma has, you must take those symbols to form a string. You don't need to take all the strings, but whatever the required symbols you have, required to form a string. What are the symbols you require to form a string? You must take to form a string. Let's talk about sigma, which is very famous in our subject a comma b or 0 comma 1 or x comma y. It's called as binary alphabet. What is it called as? Binary alphabet because it has two symbols. Let me take the very simple string which is called as empty string. Oh, there is a one word which required to understand empty. That is, empty word can be used in various places, but all the places it not be same. Like empty set is different, empty string is different, empty language is different. So you must aware what are these different words we use along with the empty. So empty string, nothing but it is a string which has 0 sequence of symbols. So when I don't write any sequence here, that's called as empty string. So to define it, I don't have a, I don't have a b in this empty string. So we denote with epsilon. Sometimes we represent with lambda. But remember, epsilon lambda is a symbol from some other place, but here it is not a symbol. The symbol is a and b. Remember, these are the only two things which are called as what? Symbol. A is a symbol, b is a symbol. But this epsilon or lambda denotes empty string. And never call this epsilon lambda is a symbol in alphabet. No, unless they mention it. But here the epsilon lambda is called as empty string. What is the meaning of empty string? If I denote the string is with w and this w is epsilon, length of w, if you try to find out, it is 0. You should never say it is 1. Remember this point? The length of the string is 0 because there are no symbols in the empty string. To denote there are no symbols, we have epsilon. So now onwards, whenever I take epsilon, you must assume there is no symbol in that string. That is how you define epsilon. Okay. Next, what else you have? The strings over the a comma b. And if I take length of the string is 1, if I have the string with one length, what are the strings you can form here? The a and b itself, they are one length. A and b, they are one length. And there is another definition of alphabet. Alphabet is set of one length strings. I call it a set of symbols, right? But symbol is another definition. Symbol has another definition. It is the one length string. Anybody saying symbol, remember this point, symbol is actually same as one length string always. What are the symbol you see? That has to be one length string. Okay, so in the strings, whenever I write a symbol, that's called as one length string. Fine, that's why I have written A and B. Then I will move to two length strings. Tell me what are the two length strings you know? Like, what is the meaning of two length? It is a sequence of two symbols. That means one after other. Suppose A followed by A, it's a two length. A followed by B, again two length. B followed by A, B followed by B. That's all you can form using given sigma. Sometimes more than these four strings possible if the sigma has more symbols, right? If the sigma has only one symbol, let's say A, then how many two length strings you can form? only one, that is double A. There is no other two length possible here. AB you can't write because sigma is not having a B. So this is all you require to learn what is the sigma and how do you form the string from the given sigma. I hope you got a clarity with two length. Similarly, you can form three length like AAA, AAB, all possibilities, BBB. So how many three length strings are possible over the given sigma which is having two symbols? Remember what I am saying here. There are three positions you have to keep, and each position could be any symbol from the given sigma. Like if I want to find out how many strings here, then you should take like combinations. You have three positions and each position is having either A or B, but not both at a time. Impossible, right? You can't keep both at a time. Either you can keep A or B in the first position. Again, similarly, you have two choices, A or B. Here also you have two choices. So if you try to form the number of three length strings, how many number of three length strings here possible? Number of three length strings, which is equal to two possibilities, and multiply with 2 and 2, you will get 2 power 3, which is equal to 8. You got 8 right. In general, how do you form? Anyhow, we'll solve again in the questions, but I want to give you what kind of questions we can expect in the exam. So they will give you in general, I'm just forming it, length of sigma is equal to, let's say, n. So I have n symbols in the sigma. Now I want to form k length strings. How many k length strings are possible? I want to form k length strings. How many k length strings are possible? Can you find out the number of k length strings? Can you use this formula? Here, what do you mean by 2? 2 means two symbols. In place of 2, what do you get? N. And in place of 3, you will get number of k length strings, right? So it's equal to n power k. N power k. Is that clear? N is the number of symbols in the sigma. K is the what is the string length that you want to form. And total number of k length strings possible over n length alphabet, over n, size n, or you can say, or n number of symbols in the alphabet. So that is n power k. So you may note down that how many k length strings possible over n symbols, which is equal to n power k. Fine. So this is how you can find out the strings over the given sigma. Now let's move to some of the questions which you require. Here the questions are possible like operations. Do you want to know some of the operations? Let me write some of the operations over the strings. What kind of operations you may try? Like the first one, which is maybe important, that is concatenation. Second, sometimes you may come across a reversal of a string. Of course, already I tried the length of the string, the number of symbols in the sequence. Likewise, you may apply a lot of different operations over the strings, but I have just taken the few operations. What is the concatenation? Let me try. Suppose I have W1 is AAB and W2 is, let's say, BA. Then I may form the W1 followed by W2, or I may form W2 followed by W1, or I may form W1 followed by W1, or I may form W2 followed by W2. There are various ways to perform the concatenation over the given two strings. Like I may take the same string twice or different strings in different order. So if you say W1 followed by W2, it's just a sequence. First you take a W1 followed by W2. And you may wonder, so if the length of the W1 is 3, length of W2 is 2, then what is the total length? Which has to be 5. That means 3 plus 2, which is 5. Okay, so this is a very important factor, length of W1 plus length of W2, which will be length of W1, W2. And similarly, length will be same. 2 length first, BA, and then followed by 3 length. So again, you will get 5 length. Here when I ask, is it always length of W1, W2 equal to length of W2, W1? Always. But W1, W2 need not be same as W2, W1. The strings need not be same. Remember that? maybe same in some situations, but sorry. In general, the W1, W2 need not be same as W2, W1. This is called as commutative property over the concatenation. So we'll also discuss this point, but remember this symbol is need not be equal. So remember this point too. W1, W1, which is 3 length, right? 3 length followed by 3 length, which will be 6 lengths. Some people may write this as, if you want to represent some other way, AAB square. So this square is not mathematical square. This square is over the strings. So it's a repetitive. So AAB, when you repeat twice, you can also write in the form of AAB power 2, which represents same as AAB followed by AAB. Now W2, W2, right? BA followed by BA, you can also represent as BA power 2. So this is how you can do the concatenation over the strings. Similarly, let's talk about the reversal of a string. Here I am always taking, remember the sigma is A comma B. When I change, I will definitely mention in the slide itself. Now let's come to the reversal. Reversal of a string. How do you perform the reversal of a string? Which is straightforward. Suppose I have AAB. What should be the reversal? Reversal you may write as W power R, which is same as reverse of W, which is BAA. So instead of writing in this left right, now you will change the direction right left. So you will get BAA. In case if W has length, let's say N or K, anything, then what is the reversal of a W? Is always N. W and W power R need not be same. Remember that W and W power R may or may not be same. It depends on the sigma and it depends on the string. Now you may ask, sir, in what situations these two are same? Yes, when I take a palindrome like W is ABA, now do the reverse, you will get the same. When you write in the reverse order, you will have the same. So when you have the concept of palindrome, W and W power R will be same. What are other situations you may face it? When the sigma is having only one symbol, let's say A. In this case, write whatever the W is always same as reverse of the W. This is the one more important point. The W and W power R is always same when the sigma has only one symbol. You may check. W is equal to, let's say, EE. Now write in reverse order because all the symbols are same. You write in any direction, you will have the same, right? Which is W power R EE. Clear? When you have more than one symbol, there is a chance to have a different sequence. You will have a chance. But sometimes you may have the same sequence if the string is palindrome. Fine. So this is what the reversal of a string. The length of the string is always same as length of the reversal of it. Now we have seen the concatenation and reversal. So what is the next one we have to see? The length of the string. I hope you no need a special slide for that. Length of the string we already seen, we were talking about it. The length of the string is nothing but the number of symbols in a sequence. So let me take an example here. What is the length of a string? Suppose W is equal to AAB. So what do you mean by length is just 3 symbols in a sequence. We will write just 3. Length of the string is 3. Fine. We have come across the definition of a string and few operations over the string. Now it's time to learn some of the questions over the string. There are various operations that I will discuss through the questions. Okay. The first question is, which of the following is not a string over the alphabet A comma B? So we have 2 symbols in the alphabet. That is sigma A comma B. Empty string. Is it a string? Always. Over any sigma in the world, the empty string is always a string. Fine. Now the question is, which is not a string, but this is the string. And AAA, yes, it is a 3 length string, right? This is a 0 length string. Fine. There's a 3 length string which has a meaning, but this AB in the square brackets, in the curly brackets, sorry, in the curly brackets or any brackets we mention here, that's not a string, right? It is a set here. This one is called as what? It is a set, not a string. Set, it is not a string. How do you know it is not a string? Because the A and B are only symbols. Anything you write in a sequence, it has to be A or B. This curly bracket should not come in a sequence, right? You can write AB, this is a string, but this is not a string. Okay, so this point we want to choose not a string, so this is definitely not a string. Okay, you may ask, so what are the situations you may face not a string? Clear? So when you write a string, you always remember you can't keep something like this. Infinite string, especially this should not come into the part, as a string is always a finite. By definition, in theoretically this is a string, infinite string, but you should never write in the computation. So this should not be considered as the computational string. So this is a very special, we don't write in any language. What we write, we'll see in the language definition, how to form the string in the language. Fine. So we got the answer, that is the C is not a string, it is actually a set which has a string. How do you speak? It is a set which has a string. But other two, A and B, are straight away they are strings. Okay, next question. Find number of 3 length strings over the alphabet. $1. Don't surprise. These are the 3 different symbols that I need in my language. So I have formed the alphabet $1. So here we have 3 different symbols. $1. Now you need to form the 3 length strings, right? So you require a concept of formula that can give you direct number. So I already explained how many symbols are there. The size of the sigma is 3 instead of n. So I already mentioned it is n. Now if you want to find number of k length strings, you can use that if you have remembered it. Otherwise you can form it. Number of k length strings is equal to, what did I mention? N power k. Because each position you will have n choices, there are k positions total. So n power k. Now n is here 3 and k is here also 3. So no confusion, n is 3, k is 3. So 3 power 3. So which is the right option for you? 27. This is how you calculate number of k length strings over n symbols. A number of 3 length strings over 3 symbols. Fine. How many prefixes are there? Okay, this is another kind of operation over the string. So now first you should know what is a prefix. Then only you can find how many prefixes are there for the 3 length binary string. Binary string, when they mention the alphabet is given to you. Binary, it mentioned that sigma is having 2 symbols. You may mention 0, 1, or you may mention A comma B, or you may mention X comma Y, but keep 2 symbols in the sigma. Now I'm assuming it's a very famous for us binary language, digital, right? In the logic we use the 2 symbols 0 or 1. Now how many prefixes are there? Before that, what is a prefix? What is the prefix of a string? Let's say string is 101. I have taken 3 length string to understand easily. What are the various prefixes that you can write over the W? Prefixes of W. What are the things you can write? You know, in this string, whether you take prefix, suffix, substring, any kind of operation over the string like subsequence, anything, you always follow left to right. But where do you begin, where do you end, and what do you take? 3 things are different. Where do you begin and where do you end, and what symbols you consider in the sequence from left to right? Remember, these are the 3 points are important. So in the prefix, where do you begin? Begin is always in the first position here, before the first position. Where do you end? Doesn't matter. So beginning is already fixed in prefix. End is anywhere. So I have the choices to end. If I begin here and end here, you will have epsilon. So epsilon is very special prefix of the any string. You take any string in the world, epsilon is always a prefix to that string. Next, what else you can write? You can start before 1, you can end after 1. That is sequence of all the leading or beginning symbols of the string. The sequence of all the beginning. See here, epsilon is there, 1 is there, and after 1 you can have 0. See, I cannot take 0 directly. Why? Because beginning is fixed. If you want two symbols, you can go up to 0. If you want 3 symbols, you can go up to 1, 0, 1. So these are the prefixes are possible for the given string. Now you may have doubt. Sir, I have 3 length string. How many prefixes I can have? Total 4 prefixes. These are how many are there? 4 prefixes. Now it's very easy to answer. How many prefixes are there for 3 length binary string? It's not only 1, 0, 1. You can take any 3 length, 3 consecutive zeros or 1, 1, 0. Anybody you take, you will have 4 prefixes, but prefixes might differ, but number of prefixes will be 4 always. So now you can answer easily for the 3 length binary string, how many prefixes are possible? How many prefixes are possible? That is 4. Okay, sometimes you may have answer 3 other things. 3. When will be that? That is the next question. How many non-empty? So remember this, non-empty prefixes. That means exclude epsilon. It means prefixes excluding epsilon. You can't include epsilon now. Previously, when I asked how many prefixes, epsilon was included. Now you can't. Now I'm just taking again w is equal any 3 length 0, 0, 0. Now what are the prefixes are possible? Prefixes, one is epsilon, but that you can't take now as non-empty prefix. You require this is empty. This is empty prefix or empty string, you can say. Now 0, 0, 0, 0, 0. So how many you got? 3 non-empty prefixes. So you will answer now 3. So I hope you have a difference now. When they ask non-empty prefixes, exclude epsilon. When they ask number of prefixes, include epsilon. So in general, you can write a concept now. When the length of the string is n, or let's say k, assume w is a string, then first point, number of prefixes is always k plus 1. Number of non-empty prefixes k, where that one epsilon is deleted. So this is how you can form the prefixes. Similarly, you can also learn suffixes, substring. Let's look at some of the important operations. How many suffixes are there for 3 length binary string? Now what do you mean by suffix? As usual, let's take the string suffix of a string. Let me take a first string, then I'll find the suffix. 0, 1, 1. Now what I told in prefix, the beginning was fixed. Here in the suffix, ending is fixed. Now where is the begin? That's your choice. But sequence is always from left to right. So it's a sequence of ending symbols, or trailing symbols. Now, what are the suffixes you can form over this W? Now if I start here itself and end here itself, you will have an epsilon. That means I have not considered even one symbol in the sequence. Then if I consider one symbol in the sequence, that is only the last I can have. If I consider 2 symbols in the sequence, I have to end here, so I can begin after 0, then you will have a double 1. Then if I want to consider all the symbols that I want to begin in the beginning, then 0, double 1. So these are the possible suffixes. These are the possible suffixes for the given string. So again, how many suffixes you have? 4 suffixes. When you have the 3 length string. For the given 3 length strings, you will have the 4 suffixes. This is how you can calculate. Now onwards, you can easily answer it. How many suffixes for the given n length string? N plus 1. How many prefixes? N plus 1. So number of prefixes, number of suffixes will be same, but prefix suffix need not be same. Okay, remember that point too. Now you can make a formula like, the answer is here 4. Similarly, if I ask non-empty suffix, same. Now I'm not going to mention it. So total you have now 3 instead of 4, where epsilon is ignored, So I'm just writing, if the length of the string is k, then you may write the first point, the number of suffixes, same like prefixes, which is equal to k plus 1. And second, number of non-empty suffixes. That means exclude epsilon, which is equal to k. I hope you got a clarity. What are the prefixes and what are the suffixes over the given string? And the count is always same when you're talking about number of prefixes or suffixes, but only the strings may vary. Okay, very interesting question. I have seen nearly 3 gate questions based on the substrings. Of course, there are questions on prefix suffix too, but the majority questions are based on substrings. Why this is very important? In prefix and suffix it was so easy because one thing was fixed and you always go from left to right in a sequence, so it's very easy to form. When it comes to substring, what is the substring first? Before answering this question, what is the substring first? Substring of any given string. Right. So given string, let's say 0, 1, 1. Now you can try to understand the substrings. It should be the part of the string somewhere. But part doesn't mean that, suppose I have here instead of 0, 1, 1, here you have a 0, 1, 0. 0, 0 you can't write, it is not a part. Part means it should be there somewhere and should maintain a sequence. 0, 0, both symbols are there but not in the same sequence, right? After 0, another 0 is not coming. So you can't take such a thing as a substring. Now, what do you mean by substring? It should be the part of the string somewhere. So now, what part you want to consider? Sequence has to be left to right, and you can take any part. Let's try. Substrings. What are the substrings possible? Epsilon. You may ask, sir, I can't see epsilon, but epsilon is there everywhere. Right? After 0, so many epsilons are there. In between 1, 0, so many epsilons are there. In between 0, 1. That's what the epsilon property and behavior, that epsilon means I am not considering any symbol. That means epsilon is part of it, but it is 0 length string. Now, 0, how do you get 0 from this string? There in many places. You can take from here or you can take from here. 1 length string, I can take it as a part of the string. So this 0 is a part of the string but appeared in various positions. That's fine. It could appear in more than one place. This string could present in more than one places. Right. Next, 1. Is it present? I'm concentrating on 1 length first. First 0 length I focused. Yes, there. And 1 length is also there. So this one is present at one place. That's fine. Now 2 length. When you write 2 length, what do you write? 0, 1, because that's there in this position, in this part. And 1, 0, it is there here. But you can't write 00. That is what I am saying. 0, 0 is not a substring. But this comes under, if you study algorithms, this is called as a subsequence. You may skip some symbols to get this 0, 0. I'm going from left to right. If I skip this one, I'll get 0, 0. So this is called a subsequence. So I'm not talking about that. But right now, it is not a substring. 0, 0 is not a substring. What else we have here? 2 length, I have considered all the possibilities. And then 0, 1, 0. 0, 1, 0 is a 3 length substring. So these are the possible substrings. Right? But you may wonder now, how many substrings? How do I find out? It's a very difficult. As you know, how many substrings are there for 3 length binder string? It's not unique. Why it's not unique? Let me take one example. Let me take 0, 0, 0 and 0, 1, 0, 0, 1, 1. That's all enough. There are so many, right? So I'm just considering these 3. Let's say these are the 3 different strings we have. Your question is here, find the number of substrings. You are trying to find here substrings. You're trying to find here substrings. For this 3 consecutive zeros, what are the substrings possible? It should be the part of the string epsilon, 0, 00, 000. That's it. You can't get more than this substrings. Now, when you take this epsilon, 0, 1 and 0, 1, 1, 0, just now we have tried, right? 0, 1, 0. Now, when you compare these two, here only 4 substrings are there. Here, 1, 2, 3, 4, 5, 6. Here, 6 substrings are there. And what else here? You can see here, epsilon, 0, 1, 0, 1, 1, 1, and then 0, 1, 1. Here also you have 6. But sometimes you may have more too. Suppose, assume that your sigma is having 0, 1, 2. Then what else? I'm just saying that sigma is, let's say, 0, 1, 2. 3 length, you may write 0, 1, 2 also, or 2, 1, 0, or 1, 2, 0. All the 3 symbols are different. In that case, if this is W, this is a special example I am taking. For this, epsilon, 0, 1, 2, and 0, 1, 1, 2, and then 0, 1, 2. You look at now, 1, 2, 3, 4, 5, 6, 7. 7 substrings are there. Then how do you get this point? Clear what I am saying? So for a particular sigma, this number of substrings for the any length is going to vary. See, for the 3 length only, you get a different answers. Like here you have 4, here you have 6, here you have 7. It depends on the sigma, how many substrings are there. So what I say here, that depends on the string, the number of substrings will vary. So I'm going to make a formula for that. Sorry. If you want to find the number of substrings, there must be lower bound and upper bound. The lower bound is always possible when all the symbols in the sequence are same. Like when you have W is equal, let's say 0, 0, 0. Then what are the substrings are possible? Epsilon, 0, 00, 000. How many you got? 4. How did you get? If 3 length string is given, you have the 4 substrings. So if n length, number of substrings for, let's say, n length string, then you will have, for n length string, you will have n plus 1. N plus 1. But how do you form this? So let me take that example, because I do not know what is the sigma given. So definitely I have to assume the sigma is, in general, could have a different symbols in a sequence. So W, I'm taking something like 0, 1, 2. If the sigma is given, the formula is going to change definitely. So here sigma is not mentioned. So I'm just considering all the symbols in a sequence are distinct. Distinct symbols in a sequence. There is no repetitive symbol at all. In that case, you will get the maximum number of substrings possible for the given string. So how many you will get? So here, epsilon, 0, 1, 2, it's a 1 length, right? 2 length, how many you get? 2 you get. 3 length, how many you get? Only 1. So I'm just making a formula. For a 3 length string, you have total 7. How do you get this 7? See, when you have 3 length, there are 3 substrings with 1 length. So this is, in general, if this is n, let's say n length means the n is equal to 3 here. So if there are n symbols which are distinct, you will have n substrings here, right? 3 substrings here, 3. N means 3 here. Remember that? N means 3 here. And here how many you have? N minus 1. 3 minus 1, you have a 2 substrings. Here how many you have? N minus 2. Keep on going till 1. This 3 minus 2 is what? 1. Actually it is what? It is 1. So I'm just mentioning in the square bracket. This is actually 2. This is actually 3. So additionally you have epsilon. Epsilon is there for every string as a substring. Now 1 plus 2 plus 3. It's going to make a summation formula like 1 plus 2 plus 3. N into n plus 1 by 2. If you remember this concept, sigma n concept. So in general, this will form sigma n, and additionally this will give you 1. So sigma n plus 1, that is n into n plus 1 by 2 is a sigma n plus 1. You can also write as sigma n plus 1. When do you get? When all the symbols in the string are distinct. That is the case. This is how you can calculate And remember, don't answer uniquely always this one or always this one. There are special conditions for lower bound and upper bound. If the condition is already given in the question that number of substrings for the given end length string where all the symbols in a string are distinct, then you just go to this answer, right? There is one more question I am asking, number of non-empty substrings. When I ask non-empty substrings, just delete epsilon here, epsilon here. So here you will get n and you will get sigma n, that's it. So plus 1 will not be there when the question is number of non-empty substrings. So I hope you got a clarity. Let's come to this question. What do you have? How many substrings are there for 3-length binary string? Impossible to answer like this. So you will go for none of this because the question has two answers, lower bound and upper bound. The answer could be anywhere in between, right? So that's why you can't answer uniquely. There is a range, minimum answer and maximum answer will be there, but not like a particular number for this. Let's move to the another question. How many non-empty substrings? As usual, non-empty substrings. I just told minimum you will have n number of substrings. Maximum you will have sigma n. So for this question, for 3-length binary string, you will have a 3 minimum. Maximum, that's 3 into 3 plus 1 by 2. That will be 6. So this is a maximum. The answer should be somewhere in between 3 and 6 in between. That's why these options cannot be correct. So I hope you got a clarity why we answer none of the above. The reason is you can't answer a unique number for finding number of substrings as you have the different answers. Okay, how many different length? Oh, this is completely different question which was asked in the previous gate. How many different length substrings are there for 3-length binary string? Now, what do you mean by different length? Let me ask the question again. Suppose W is, let me take 0, 1, 2. Of course, it's not binary strings, right? The question is very simple. Okay, if you are going for the previous questions, that's about binary strings. You should be very careful. Binary strings, you have only maximum 2 symbols. Maximum 2 symbols. So this formula could change. Instead of sigma n, could change. Because I mentioned the binary string, so symbols will repeat. Symbols definitely will repeat. So this is not the maximum answer at all. So in general, I have taken 3-length string, but when it is binary, the answer will change here. So I want you to calculate it, but be careful. In general, the question will be for 3-length string. I modified to 3-length binary string. So be careful about that formula. Okay, now how many different length substrings are possible for 3-length binary string? Now let me take 3-length binary string. Okay, so I'm just taking 0, 1, 1. Now how many different lengths are there? This is W. Epsilon, 0, 1 and 0, 1 and 1, 1 and 0, 1, 1. When you are talking about different lengths, I'm not talking about different strings. If I ask different strings, for this string you have a 7, 1, 2, 3, 4, 5, 6. You have a 6 here, right? For this string you have 6 substrings. But different lengths. You take any string from 3 length, you will have a different lengths are same. Here, how many different lengths? Different lengths. Different lengths. How many different lengths? 1, 2, 3, 4. This is 0 length. These are 1 length. These are 2 length. These are 3 length. These are the lengths I am calling. Length 0. Length 1. How many different lengths? 4 different lengths. So different lengths are 4. Different strings, how many for this? Could change. Different string, different substrings I'm calling about. Different substrings. How many? 6. So my question is about different lengths, not number of substrings, number of different lengths. So here number of different lengths or different length substrings, how many are there? 4. Now my question is very simple. I'll just take 000, 001, 010, various different 3-length strings I am taking here. So now find different lengths. Different lengths. How many are there? different length substrings. Here how many will be there? 4. Here how many will be there? 4. Here how many? But number of substrings may vary. As it's told, number of substrings may vary, but number of different lengths are same for all. 4 only. Here 0 length will be there, 1 length. The 4 doesn't mean that 4 strings. Remember that. 0 length, 1 length, 2 length, 3 length. Here 0 length, 1 length, 2 length, 3 length. Here also you will have 4 different lengths are there. That's why you get the answer 4. So how do you get the 4? Just calculating different length substrings. Now you answer it for the 3 length. Doesn't matter binary string or ternary string, any string. If it is 3 length, how many are there? Oh, it's not there here answer, right? So none of the above you go, but answer is here 4. Now one more question, which was actual gate question. How many non-empty, that's other than the 0 length, how many different length substrings excluding 0 length? If I exclude 0 length, the answer will be, rather than 4, it will be 3. That's it. So if you include all the lengths, you will have a 4. If you include other than the 0 length, you will get a 3. If you exclude 0 length, you will get a 3. If you include 0 length, you will get a 4. This is one of the famous gate question which was asked, but that is not for the binary, that is in general string that could have any sequence of symbols. Fine. Now we'll move to the language. So far I have explained what is a string, what are the operations of a string. Now let's come to the language. You have an alphabet, then you have a string, then we will have a language. So as I told, without a sigma, you cannot form a string. Without a string, forming a language is difficult. Then why do you want this language? To specify or to represent the problems. All the problems we denote or represent with the languages. That is why you need to know the sequence. The sigma has symbols. Using those symbols, we will form the strings. Using those strings, we will form a language. So if I have the certain set of the strings in the language, you can represent a problem. Like I want a problem where I want to solve the length is divisible by 2. Then I'll represent to the language. So we'll get to know slowly. Now let's come to the language. What is a language? You see that language is a collection of the strings defined over the sigma. What is a language? It is a collection of the strings. What are the strings you have understood? You collect all those strings. Collection of the strings defined over the sigma. Sigma here alphabet. Now what kind of languages you can form? Let's see. My sigma is A comma B. The strings, how many strings are there? If you ask me, so many strings. I can't say 10, 100,000. Infinite strings are there. Can you write some of them here? Yes. What are the strings are possible here? Strings. Epsilon, A, B, 2 length, 3 length, so on, right? You keep on writing, you will never end up. But you can write all the strings in a sequence till infinite. Okay, these are the strings. There are infinite number of strings possible, but every string that you write has to be finite. So this is a very important terminology in theory of computation. Every string should be finite, but such finite strings can be infinite. Remember that point. Okay. Now what is the language? So many languages are possible over this sigma. What are those languages you can write? Here, the one language could be empty language. What is this language? Specialty of this language is I do not have any string to represent in my language. My problem specifies I don't want anybody to present in the language. Then this is called as empty language. You may represent with empty set the pi. This is called as empty set or empty language. Represent, there is no string present. Even epsilon is also not present in this set. Always we represent the set with the curly brackets. Now, is there any other language? Yes, I may have only a singleton language. It's called as what? Singleton, where only one string present. I may have even epsilon. Oh, that's good. It is also singleton language. I may have only B. I may have only AA. I may have only AB. Such singleton languages are infinite. It's not 1, 2, 3. You can write this is only the string in the language, right? So let me mention some of the strings here. First I mentioned empty, and then epsilon. These are all languages. You can mention L1, this can be L2, this can be L3, and so on. L4, B, and L5, let's say double A, L6, AB. These are singleton languages. So many are there. Now I'm going to write the languages which is going to have two strings like epsilon A or epsilon B or A comma B. Oh, it looks like alphabet, but that is also a language because that is a set. And A comma double A. Likewise, how many you can write? So many, right? So many. Infinite languages you can write with two strings. What else you have? You can write 3 length, 4 length, 5 length. You can represent when you have more strings, right? You can represent like I have a W such that the W is belongs to a very special notation A comma B whole star. Okay, that's not important right now, but I'm just mentioning it. What is the meaning of this? Before this, I have mentioned something like A comma B whole star. Here in these languages, the A comma B whole star represent all the strings that you have, like epsilon, A, B, double A, every string present. That's called as basically universal set. What is it? Universal set. You may ask, sir, why do you represent this way? Because this set can be repetitive any number of times with the help of star. This star is basically called as Kleene closure. So you may ask, sir, how do you generate all the strings? This A comma B whole star, it means A comma B power 0 or union, you can say A comma B power 1 union A comma B power 2, which is going to give you all the length strings. Like A comma B power 0 means take 0 length string, means epsilon. A comma B power 1 means A comma B only. When you write A comma B power 2, you will have a different meaning here. So let me explain here. A comma B power 2 means repetitive, 2 times you repeat with the concatenation, which gives you all the 2 length strings. See that A dot A, which is going to give double A, comma A dot B, B dot A, BA, and B dot B, which is BB. This is how you get all the strings which are present over A comma B. Here all strings are present. So this set is called as universal set, also called as universal language. Now, what is the meaning of this? W belongs to A comma B whole star means W is any string over A comma B. Instead of saying W is anything, we are writing W belongs to A comma B whole star. So what is the meaning of this set notation? All the 2 length strings are required, which is exactly same as what I have written here. AA, AB, BA, BB, because I want 2 length only. So AA, AB, BA, BB. That's it. This is this notation I have taken from the set theory, where set theory you have set builder or set roster notation that can be used to form the strings or elements of the set. Your element is nothing but a string. Okay, there are various ways to denote the set. So I've used one way to denote. Why I'm using it? Because writing all these strings are very difficult. If I ask, suppose length of W such that W is any string over A comma B, which is easy to write. Length of W is 100. Can you write all the 100 length strings? Very, very difficult. But this notation will help you denote, oh, this language has all the 100 length strings. But in case if you want to write, maybe this board or this slide is not sufficient to write all the 100 length strings. That is the beauty of this set notation. I hope you understood what is a language. Language is a collection of the strings. That strings may not present, or may present only one, or may present only 2 strings, or may present any number of strings, right? The language may present any number of strings. Based on this, I can tell you the language is 2 types. One is the finite language, other one is infinite language. What do you mean by finite language? When the number of strings are finite, then the language is finite. If the number of strings in the language are infinite, then language is infinite. Okay, let me just mention it. The language that we have defined so far is two types. One is the finite language, also called as finite set. Another one is infinite language. Very simple. We always use a finite string, but language can be two types. Remember this point? We use only finite string. String has to be finite, but language can be finite or infinite. When the language is finite, it should contain number of strings should be finite. When the language is infinite, the number of strings should be infinite. But in this language and in this language too, both should contain only finite string type. Example, suppose I take A comma AB. Here each string is finite, but how many total strings? 2. So it is finite language. Here infinite language, A, double A, triple A, and so on. Here see, every string is finite, but total strings are infinite. This is how you would say finite strings only there. Each string is finite, but such finite type you have infinite. So this language is called as infinite language. I hope you got a clarity what is the finite language and what is the infinite language. And let me give you clarity before going into the actual topic. So here symbol is always one length string, no doubt about it. One length string. You will never have two length. Symbol means one length. And string is actually two types in general, finite string and infinite string. But in theory of computation, we never use a word infinite string. So this is not possible. String means we always take finite string. We always write something epsilon, A, AB, but you never write A, B, A, dot, dot, dot. This is impossible. You must mention like a real number. Real number will never, sometimes you can represent infinite length, the number itself, but string itself you can't represent infinite. So we don't use in computation at all. Okay, this string is infinite actually, but we don't use in computation. Okay, and language is two types, finite and infinite. That's possible. Finite language and infinite language. That's great. I've just shown that. And in case if you want to represent infinite language, there are various examples. So let me show some of them. Like I want to represent a power n such that n greater than or equal to 0. It's going to represent infinite language. How do you know that? See, a power 0, a power 1, all the possibilities when you write, it's going to form infinite number of strings. A power 0 means epsilon, and a power 1 means 1a, a power 2 means 2a's in consecutive, and 3a's in consecutive, and so on. And this notation is going to represent infinite language. A similar notation also you can use for finite language, like I mentioned, a power n such that n less than 3. Then up to 2 length you can keep in the language. Up to here, then language will be finite. This notation can be used for both finite and infinite languages. Sometimes we write in sentence, sometimes we represent the string, sometimes we write in set notation. We all are actually equivalent to understand what is the language. Okay. Now let's come to the point. So now we have understood what is the language. How many languages are there over binary alphabet? Binary alphabet in the sense sigma has 2 symbols. How many languages are there? Finite, infinite, we can't determine, and none of this. So guess what is the right answer for this? If it is the finite number of languages, then definitely you can't write infinite number of strings, right? In general, for any given sigma, you have infinite number of strings. Strings already infinitely possible, right? Then language definitely you can form infinite. So the answer is infinite. I've just shown with one length only, the language which has one string, like this only you can form infinite. Why do you want different languages? With one member, with one string, the language has only one string, you can form infinite languages. No need to worry about the size 2 or 3. Okay. This is how you can say, just understand how many strings are there. Infinite strings. Each string you put in a set, singleton sets only, there are infinite. Okay, very simple. Next, which of the following is a finite language? Can you identify using the mathematical set definition? Of course, we are going to come with these notations many times in future, but this time, which language is going to be finite here, and which language can be infinite? So understand here, n less than or equal to 3. So here, n value up to 3 you can substitute here. That means I can write here a power 0, b power 0, because both are equal, right? N only. Another one, a power 1, b power 1. Another one, a power 2, b power 2. Can I write a power 3, b power 3? Yes, but you can't write a power 4, b power 4. As you know, this both powers are same. That's why you can't write differently. Some people might write a power 0, b power 1. That's wrong, because both powers are representing the same variable. Now, how many strings are there? Only 4 strings. What are they actually? One is epsilon. A power 0 followed by b power 0 means 0 symbols followed by 0 symbols, that is epsilon only. Next, AB. A power 2 means AA, b power 2 means BB in a sequence. And similarly, 3 A's followed by 3 B's. That's it. So definitely, this is what a finite language. So as per the question, we got a finite language, but you need to identify it could be MSQ type. You don't know, right? N greater than or equal to 3. It starts from the 3, but there is no end for it, right? 3, 4, 5, 6. You keep on writing it, infinite strings possible. Here you will have a power 3, b power 3. Is there any end for this language? No. You keep on writing, you will have possibly infinite strings. A power 6, b power 6, and so on. No end, right? So this is infinite language. And now n less than or equal to 3 is fine. That could form possibly finite number of b's. But the a's, number of a's is already starting from 0, but it can have any. So this is the key. The a's here can have any number, like no a, 1a, 2a, 3a, 4a, 5a, and so on. Even though b's can be 0, 1 or 2, 1, 2 or 3, but a's are any. This could represent infinite set. So this b and c are infinite. A is only the finite language that you have. Fine. This is how you can identify. Of course, these questions are very easy, and without this, the TOC could see a different way. That's why I'm trying to cover in the basics what is a language, how do you understand a finite language. So this can help you a lot. Now we know languages, and if you want to know some of them, okay, like operations, I'll just tell you before going to the Chomsky hierarchy some of the operations. Anyhow, the closure properties, we will talk about these operations much. Language operations. Suppose I have one language, L1 is equal, let's say, A comma B, B, and L2 is equal, let's say, B comma B, B comma B, A, A. So I have two languages. What are the operations you can do over these languages? One is, let's say, union. Very simple. What do you mean by union? If I do L1 union L2, we'll combine all the strings from L1 and L2. You may get like A, B. I'm combining both. Like set union, definitely. Here double B is appeared twice, so you take only one, because in the set, the string cannot be repeated in the language, right? Now, second, intersection. You will talk about these operations in detail in closure properties. Just I am defining what is union and what is intersection. L1 intersection L2. What is L1 intersection L2? Which string is common? Double B is common in both of them, so you will get double B. The common strings of two languages is only double B. This is how you calculate intersection of two languages. Intersection of two languages. And what else you may have? You may have difference, set difference, or language difference. What do you mean by this? L1 minus L2. From L1, delete the strings which are there in L2. Again, from L1, delete the strings which are there in L2. So which string is there in L2? Double B. So delete it, you will get A. So here A comma double B minus B comma double B B double A. Answer always depends on L1 only. But those strings which are present in L2 will be deleted. The answer will be only L1. Okay. If A also present here, then you will get empty set. Look at that. What is set difference? Similarly, you have lot of language operations like complement. You will have symmetric difference. All these properties or operations will be covered in closure properties. I hope you have understood the strings and string operations, language and language operations. All these are going to help in theory of computation in various places to understand the behavior of the languages. To begin with this theory of computation, let me begin with what is there in this theory of computation, that is Chomsky hierarchy. So in the beginning, in the end, at all the time, you are talking about the Chomsky hierarchy only. So in the Chomsky hierarchy, all the languages are well classified and related one language with other language clearly. Here, what are those classes present here? How many classes are there as per the Chomsky hierarchy? Have you remembered? Very simple, right? He has defined 4 classes. Okay, what are those 4 classes, right? Class, you can say type 3 class and type 2, type 1, type 0. So we have a name for each box here. Each box is not a one language, it is the set of languages. But all the type 3 languages are there here in one box. We call it as a one class. So I can say it is the type 3 class. And the green one is the type 2 class. So all the languages of one type will be placed in type 2. But some of the, all the type 3 also covered in type 2 somehow. And type 1 and type 0. The smallest number will represent biggest class. 0 is going to represent biggest one, where it is going to cover all the other 3 types or 3 classes inside that. So what are the relations and what is this types? That is what Chomsky hierarchy is. In the type 3 class, all the regular languages are covered here. Here all regular languages are covered here. What is the beauty of these regular languages? Now all the problems in the world which do not require a memory can be fit into here. That means to solve any problem, you don't require any additional data structure like stack or queue, can be placed here and you can solve with the help of this representations, like whatever the models that you have here, like Finite Automata or any other model you have here, you can use them to solve. That is the beauty of every class here. And when I cover type 2, the type 2 has a name context-free languages, including these regular languages. Every regular also covers here all context-free languages. Context-free languages. What is the specialty of these languages? If any problem which can be solved using one stack, then that problem can fit into this class, can be anywhere here, including the type 3. Okay, so all the context-free languages are fit into this type 2. So there is a relation. Every regular language is also context-free. All regular languages are context-free languages. That relation is preserved here. Okay, next, type 1. When type 1 comes, including these 2 languages, there are additional languages, all of them together called as context-sensitive languages. So here all context-sensitive languages inside. Remember, every regular language is context-sensitive and every context-free is also context-sensitive and everything inside type 1 is also context-sensitive. So this is what the difference between regular context-free and context-sensitive. But can I say every context-sensitive is context-free? Context sensitive can be here or here or here. So how can I say context free? If I am going to be here, then that is not a context free. But if context sensitive is here, yes, that can be context free. That is a context free. If context sensitive is here, that is a regular, also context free. So you need to understand, when I say context sensitive language, don't assume this one. Assume everything inside the pink color box is called as context sensitive language. So all the context languages are here, including regular language and context free. Now type 0, the red color box, it is all recursively enumerable languages. All recursively enumerable languages here. That means everything I have written, you just say that recursively enumerable languages are present here. These recursively enumerable languages are classified into here 4 types, you can say, but we will learn later on slowly. So all these languages are beautifully classified by Chomsky hierarchy based on the computation behavior. We have a different models here. Let me start with one by one. Quickly, as you know, I can't discuss all the chapters at a time, right? Okay. So these regular languages, we have a model called as a finite automata. So anything you want to represent in these languages, you can use finite automata, or you can use push down automata, you can use linear bound automata, or you can use Turing machine. So for this language especially, you can use finite automata or PDA or LBA TM, because this language is covered in all the classes. So every regular language can be accepted by finite automata, can be accepted by PDA, can be accepted by LBA, can be accepted by TM, because this is the smallest class which is included in all the classes. I hope you understood. Those people who are believing regular language is only possible by finite automata, that is wrong. Regular language is possible by finite automata as well as PDA, LBA, TM. But finite automata is equivalent to regular language, because every time you design finite automata, it only represents regular. But when you have a regular, you no need to be finite automata. So there are 2 directions. Remember, if I give you regular language, if I give you regular language, you can design any of this machine. Like I can design finite automata, I can design PDA, push down automata, I can design LBA, linear bound automata, I can design Turing machine if I have a regular language. But if I have a finite automata, that only represents regular. That regular may be called as some context free or some CSL, but not every CFL. So understand the directions, how you need to interpret properly. So every regular you can design finite automata, PDA, LBA, TM. But every Turing machine, you can't say regular, because some Turing machines can do non-regular. That is what the behavior. Every regular you can use any of this, but when I say TM, I can represent recursively enumerable, but I don't know what kind of recursively enumerable. It may be inside regular, or it may be inside CFL class or inside CSL class. It depends on the language. So I hope you got a clarity. What do you mean by class? Class is having infinite number of regular languages if it is a type 3. If type 2 class, then you will have infinite number of context free languages, which includes all the regular languages, no doubt, because every regular language is already context free. And all these relations are very important in the beginning. Later on, this will be our first topic, and then second topic, this box, and then third topic and fourth topic, and so on we will be covering. I hope this Chomsky hierarchy is going to talk about how the formal languages are classified to understand the various problems in the world. So that's what I told. If you are using regular languages, it can represent the problems where you do not require any additional data structure to solve. Then all the problems can fit into here. So let's begin with this chapter, finite automata and regular expression, as soon as possible. But before that, let me start with some questions. Okay, first question: which of the following are correct? So these relations are preserved in Chomsky hierarchy. If you understood Chomsky hierarchy, this 4 points should have a clarity, which is right or which is wrong. Okay, now which of the following are correct? So it could be MSQ, right? I'm mentioning it is MSQ. Okay, what is the meaning of this? We have 4 machines, right? FA means here finite automata. Finite automata is used to represent the regular languages. Push down automata. This is also a machine. We can design various PDAs to represent context-free languages. We have a lot of linear bound automatas, which is used to represent context-sensitive languages. Turing machine, very famous in our TOC, Turing machine, to represent all the recursively enumerable languages. Now, this order is called as expressive power order. So, what is the expressive power of the machines? The finite automata can express very small class, even though you have infinite regulars, right? So that inner box, the small box, is going to represent all regular languages. So all the languages are represented by finite automata is smaller than PDA expressive power, and all the languages that you represent with the PDA is a smaller or subclass of LBA languages. Similarly, so expressive power, finite automata is having less expressive power than Turing machine. So Turing machine is having more power, more expressive power, because it can represent a lot of languages compared to any other expressive power. This one is finite automata is less. Okay, that's true, right? It's a correct, no doubt. A is correct. What about B? Regular language. Oh, this arrow, you should understand mathematically. Arrow basically implies or is. Can I say every regular language is context-free language? Yes. Every context-free language is context-sensitive language. Every context-sensitive language is recursively enumerable language. Okay, by transitively, regular language is also context-sensitive. Regular language is also recursively enumerable. But don't write in other direction, it will be wrong, because in general that will not be correct. Converse statements are wrong. So this side, regular language implies CFL, implies CSL, implies REL. It is true. Okay. Now, look at these two sentences. Regular language means I'm talking about one language. Set of regulars means I'm talking about all the languages in the class. Both are different sentences. Both are different sentences. It's like one person and set of persons. So this regular language is one language within the type 3 class. But set of regulars means type 3 whole class I'm talking about. So I can also represent like this is the type 3 subset of type 2, subset of type 1 class, subset of type 0. Is it correct? Of course it is strictly subset, we already know it. It's equal is just to denote, but it's actually strictly subset. When it's already strictly subset, subset holds. So this is also true. Okay, set of regulars is definitely subset of set of CFLs. In case anybody using these sentences, be careful, this is the wrong sentence. Why? Regular need not be subset of CFL, because one language, other language may or may not have a relation. This is a very important factor, and in between these two, no relation is, that's fine, that's a statement only. But a regular, you cannot say it is a subset of a context free. These two languages may not have even single string relation. Sometimes one regular, other regular only will not have a relation. Forget about regular and CFL. I cannot say regular subsets regular. That's also sometimes wrong. That's also sometimes wrong. Because one regular, other regular may not have a relation. One regular language may ends with A, other regular language may ends with B. When you try to relate, there is no relation at all. So understand, regular only, sometimes you may not relate, sometimes, but these are in general statements. Regular may or may not be subset of CFL, but the set of regulars means all the regulars when you consider, it is definitely inside all CFLs. But you take one regular from here, one CFL from here, may not have a relation. Forget about others. Take two languages from here only, may not have a relation. Okay, so this is very important factor. D is wrong statement to form. Anyhow, the first three statements are correct. Now, regular language is equivalent. You can't say context-free language, because context-free language could be non-regular also, because the context-free languages could be present within the type 3 class or within the type 2 class. Now, regular language is equivalent to. Who is there to represent the regular language? One machine is the finite automata. That's true. And we have regular expression too. That's what we are going to learn in the first topic, regular expression and finite automata. So regular expression is another way to represent a regular language. If I have a regular expression, I can always represent a regular language. If I have a regular language, I can always represent with a regular expression, regular grammar. So all these are correct. So you can choose option D. Correct? So this is how you can answer the questions. CFL, context free language. To represent this language, what are the various models you have? PDA, context free grammar, NPDA. So what is this NPDA? That's what we learn in the later on in pushdown automata topic. Pushdown automata by default NPDA. So there are two types of PDAs. Like, if you talk about finite automata, let me write it. You have deterministic motion and you have non-deterministic motion. But do you really need now? No. Just I'm saying these two are equivalent because you can convert one to other to this. That's fine. That's why DFA and NFA are equivalent in the finite automata. But when it comes to pushdown automata, we have DPDA, which is less restrictive than PDA. Here, this PDA only, also called as NPDA. It's not another type. So here, PDA by default NPDA, and you can also design DPDA, which is restricted format than NPDA, and DPDA here not equivalent to this one. So here DPDA is less powerful than NPDA, whereas DFA and NFA, they are equivalent. So this is very important. PDA also called as non-deterministic PDA. PDA also called as non-deterministic PDA. And when you go for others like LBA, relation is not known at non-deterministic LBA. We don't know the relation at. And Turing motion, we have two types: DTM, deterministic Turing motion, non-deterministic Turing motion. They are equivalent again. You can convert one deterministic Turing motion to non-deterministic Turing motion, or NTM to DTM conversion is possible. Here when you look at CFL is equivalent to PDA, yes, NPDA, yes, because both are same only. CFG, yes, context free grammar. So all of them are equal. All of them are equivalent. Okay. So these things cannot be understood with the Chomsky hierarchy. When will you understand? When you write a context free grammar, when you design a PDA, and when you understand the behavior of the machines, you will get to know, okay, every PDA is non-deterministic by definition. Okay, fine. With this, we have completed the basics of theory of computation. Now we are going to begin. As the crash course, I will be covering each and every point, but at the same time, you should focus on everything that is discussed in this lecture. Some things, I'm delivering with the examples, some things I'm delivering with the problems. All you need to thoroughly understand each. In case you have any doubt, you can post your doubt below this video. I'll be replying to your doubt without any delay. So be prepare and ask doubts if you have any from this video, or any point which is related to the video. I'll be happy to help you. Okay, in the next, regular expressions. Now we will see the regular expressions. It is the first topic. So far what we have learned, it is just basics. Some people who are having the basics, they can directly start from this topic. If you already know about the strings, languages, and the Chomsky hierarchy, directly begin with the regular expressions, then start practicing it. And as I told, whenever you have any doubt, it is your responsibility to ask the doubts, and my responsibility is to clear your doubts. Let's begin with this topic, regular expressions. Whenever you see expressions, you will see operators and operands. So we have here operators and operands. What kind of operators we have, and how do we deal with them? That is the first step you should learn. Then you will know how to use the regular expressions, or how to write the regular expressions. So what is the regular expression? Regular expression is used to represent a regular language. If I have a regular expression, I can say that it represents some regular language in the type 3 class. There are infinite regular languages, so you can write infinite regular expressions too. And if I have a regular expression, then definitely it represents a regular language. So regular expression, it helps us to represent a regular language or regular set. So how it represents? Using the operators. It has some declarative way that represents a regular set. So how to declare those operators now? We have 4 operators. You can also say 3, but I classified 4 as I have the 2 operators separately, like Kleene closure and positive closure. One is the plus, which is called as OR, and second is a concatenation, and other 2 are similar mostly. One is the Kleene closure or Kleene star, other one is Kleene plus. Again, do not confuse with the 1 and 4, even though the plus is used in both the places, but their meaning is different. This plus is binary, this plus is unary, and the way we use both are different. The 1 and 2 are binary operators. 3 and 4 are unary operators. How to use them? As I told, without learning these operators, if you try to write an expression, definitely you may fail in certain situations. So I always recommend to learn these properties of the operators, then you start writing the expressions. Then you will get to know how to write an expressions and how to understand them. Sorry. Or, as I told, it's a binary operator, so you should have the 2 operands to represent this operator with the help of this operator. So one, if I say R1 is some expression, R2 is some other expression, you can use the plus in between to denote or to use this plus. Now if you want to denote the expression with the help of plus, you can write R1 plus R2. Then what is the meaning of this R1 plus R2 is either R1 or R2. But R1, R2 together you can't generate. You can generate R1 or R2. If you want to represent the language, then in that R1 will be there separately, R2 will be there separately. Then what is the meaning of that? Either R1 or R2. You can generate R1 as well as R2, but not together. Not together. We'll see with an example soon. And what is concatenation? If you want to write it, R1 followed by R2. Either you may represent dot or you can omit it. Dot is not compulsory to write. It means the R1 followed by R2. That followed by, you can represent with the dot. It is R1 followed by R2. It means together always comes, but a sequence is maintained, R1 and R2. Then the sequence is maintained, R1 followed by R2. You can't write R2 followed by R1. Remember that. By definition, R1 followed by R2. Kleene star, it represent R, it's unary, right? You can't write R1, R2 here now. You can use only one expression or one operand, or then over you can write star. It's a Kleene star of R. You can also speak Kleene closure of R, or you can say R star. But all means same. R can be repeated any number of times. The star basically defines any greater than or equal to 0. So R can be repeated any number of times. So this is Kleene closure of R. Kleene star of R. Another one, Kleene plus. Sorry, did I write Kleene star here? Okay, I just copied here. So what do you write here? Kleene plus. What is R plus? So this is Kleene plus. R plus means you just speak like positive closure or Kleene plus of R. What is another name here? You have another name here, Kleene closure and positive closure. Or you can say, I'm just writing another name here, but already have written there. This is Kleene closure or Kleene star. Another one, positive closure or Kleene plus. Other two names. Right? Kleene star you can speak, or Kleene closure, Kleene plus or positive closure. So what is the meaning of the Kleene plus or positive closure? At least one time that or should exist. So to understand the meanings further, we'll take each one separately. So I hope you understood at least the name of the operator and how do you speak it, but what is the meaning we'll get to know slowly. Okay, plus means or and used as a binary operator, so you require two operands and they should be regular expressions again. Then either R1 or R2, the how do you speak that plus, and dot is a concatenation, you speak as R1 followed by R2, and star is a Kleene closure, you can write as a Kleene star of R or R star simply. Plus is a positive closure, it is nothing but R plus or positive closure of R, also called as Kleene plus of R. Let's begin with what is this plus. With an examples to understand all these four, we'll say it. So whenever I write A plus B, or whenever I write epsilon plus A, or whenever I write pi plus A, or whenever I write epsilon plus epsilon, or A plus A, or pi plus pi, you should know what is the meaning of this expression. As you know, everywhere I am using the binary operator plus, you should know outcome of this expression, because the meaning of the expression should be understood when you write it. Sometimes it can be simplified further, sometimes you may not. So whenever it is possible to simplify, just do it. The first one you can't simplify because it has A or B. When you try to form a language represented by A plus B, it's nothing but A comma B. Here A plus B is an expression, and what it generates is just set A comma B. How do you understand? It's not possible to simplify further. Maybe if you want to write, you can specify B or A as it is commutative. The plus is here commutative. The operands you can switch if you want it. Like in the set you can write A comma B or B comma A will get the same meaning. Order doesn't matter. Next one, epsilon plus A. So if I try to understand the language generated by epsilon plus A, you can't reduce further. It is already epsilon special string and A is another string. You can't write only A, because epsilon and A are both are different strings. Some people may write like it's equal to A. That's wrong, because epsilon you can't ignore. Epsilon has to be there. It should be generated. When you don't write epsilon, that means you're losing that string. So please do not write this at all. Epsilon plus A, you may write if you want it, A plus epsilon, but you can't ignore any string. You can change the direction of change the order of the operands, but you can't ignore anybody. Fine. Pi plus A. Pi means what? If anybody writing language generated by the pi is actually empty set. Okay, this pi is not empty set, it is an empty expression. I'm using an expression, right? So don't call that as empty set. It is an empty expression. So here pi is used in different places with the different names. Sometimes pi we call empty set. Oh, this is not empty set, it is empty expression. Sometimes pi we call empty expression. But how do you know that? Based on where do you write? I'm writing along with the operands, operators, so it is one of the operand in the expressions, so definitely empty expression. I hope you understood what I'm trying to say. In the set theory, this pi represents empty set. In regular expression, it is empty expression. Okay, in general we may use together, but be careful when you use it, the meaning should understood, right? So it's expression, so you call pi is empty expression. Okay, so here you will get equal to pi, but this is empty set. Even though I write pi, but that is not empty expression, this is empty set. So language generated by empty expression is an empty set. That means L of pi is a pi, but this pi and that pi looks different, the meaning is different. Okay, so that's what the problem with these two pi's. Anyhow, the internally they are outside they are equivalent, and internally only their names are different now. Fine. So be careful with that. So pi plus A, what is the meaning now? Language generated by pi plus A. The pi will not generate even one string, so you don't get anything. A will generate one string, so A you will get. So when you get a language which has only A, you can write simply A, right? A plus pi, pi plus A, both are A only. Clear? So this is going to generate only one string A. Now pi has no participation in generating a string. Now when it comes to epsilon plus epsilon, both are same operands, right? You can simply write epsilon, both will generate same string epsilon. And a plus a is generating a, or a is also generating a, so both will generate a. What is the meaning of a plus a? Let me write that too here. Whenever you get a situation like R1 plus R2, remember the point, it's same as if I ask language generated by R1 plus R2, you just say language generated by R1 union language generated by R2. You can understand that way. If you want to understand what R1 plus R2 does, just do the union of two individual languages represented by them. So you want to understand R1 plus R2, just understand what is R1 generating and what is R2 generating, just do the union, right? That's what I am doing all the time. What pi does nothing, what a does a, so I did the union, you got this. Now pi plus pi, see, pi means it's generating nothing at all. So you will get empty set union empty set, you will get empty set, so it can't generate anything. So again pi. Clear? This is how you use the OR operator. Now we will go to the concatenation. So what is the concatenation responsibility? You have seen just now a plus a you did, now I am doing a dot a. Just think about what it does. Like a dot epsilon, a dot pi, or epsilon dot epsilon, a dot a is done, right? A dot pi and pi dot epsilon, pi dot pi. So just try to understand these few expressions which are using concatenation. A dot a, see, a plus a means both are generating a, so you said a. But when you say a followed by a, you can't say a. Why? Because it's a two length. It's going to be two length. Now this is one length. How can be they are equal? Impossible, right? But here this side is generating a and that side is also generating a. You take any side, you always get a, so you have taken a. It's just like if else condition. If go this side or else go this side. But when you do the union, you got the same thing. Then you don't need if else, directly you generate a. So that's important for the plus. But dot means you must follow. So a followed by a. You can't get a, you get double a. So you may write as a power 2. That's fine. Because a is repeated twice, you may write a power 2, or you can keep as it is double e. That's fine. Two consecutive ways. But a followed by 0 symbols, a followed by epsilon means simply you can write a. See, before a, after a, epsilon is there, that we don't write it all, because there is no importance for the epsilon when somebody else is present. So a followed by nobody is there, but that's empty string basically. So one symbol followed by 0 symbol, you will get one symbol only, that is a. So remember one more point, a dot epsilon dot epsilon dot epsilon, it's just a only, because this is just 0 symbols. And simply a dot epsilon is just a, or epsilon a is a only. So when you have so many epsilons like this, you can write one epsilon 2. As this many epsilons has no importance, writing nobody is there, right? Fine. Now a dot pi, here it is a problem. A will be generating a, but pi will generate nothing. So how can I get some string from here? Impossible, right? So this expression will never generate anything. So result is a pi, because pi acts as a dominator in the concatenation. Remember this point? Whenever you see pi in the concatenation, and whatever the expression that you are doing with the pi, is whole expression will become pi. So I say anything, pi dot anything is pi, or dot pi is pi, but don't keep pi whole star, pi whole plus. That's a different meaning. We'll talk about that. So pi dot or dot pi, or pi dot anything is always pi, because it can't generate even one string. You want to understand more about it? Yes, we can come up with that. Okay, let me take this. Now some people might trying to understand what is it. Why can't I write a? Why can't I write a? Right, the question is, a is going to generate only a, pi is going to generate nothing. Then from here you can take a dot from here you can't take anything. Then how can I form a string without taking anything? At least if you have epsilon here, a dot epsilon, you will get epsilon. So when somebody saying a dot epsilon, definitely will get a, no doubt, because here epsilon will be there. But this pi means empty set, and when you have empty set, there is no string inside. In case if you have a string here, epsilon, then you can write epsilon. So in case if I write a dot epsilon, now a dot epsilon, you will get a, no doubt. But here you get empty set. So this means a followed by no one is always no one, but a followed by empty string is always a. So understand the difference between these two. A set has no one, set has empty string. Both are different. Why? Why both are different? If you take empty set, do the cardinality, you will get nothing. But you take set and ask the cardinality, you will get a 1. And also remember, epsilon length is 0. Doesn't mean that set which has epsilon is 0. Remember, set which has epsilon means in the set how many members are there? 1 member. But size length of the epsilon is 0. Both are completely different. So have the difference between these two. Fine. Now come to the point. Epsilon dot epsilon. Epsilon. A dot pi. Oh, already asked here. So just change it if you want it. Pi dot a, which is again pi. And pi dot epsilon. See, don't look at epsilon, look at pi. Pi dominates whole expression, just write pi. Pi dot anything is always pi. So here what do you understand? That there's one point which you require to remember. Pi dot any is always pi. But don't add anything to this pi, as a whole star or whole any other. So that gives you different meaning. But pi alone dot anything is always pi, because pi acts as a dominator. This is called as dominator along with the concatenation. If you are doing concatenation, it acts as a dominator. That's why whole result will become pi. Okay. But when you do along with the plus any expression, let's say it is r, the result will be r. Why is that? Because this acts as identity. It will not have an importance when somebody is there. Identity for r operator. Okay, so identity for r operator. So pi has two significances along with the two different operators. For concatenation, it is a dominator. For r operator, it is identity. It has no importance when somebody else is there along with the plus, and pi has only importance when you do with the concatenation. So these two are completely opposite direction, opposite ways. Fine. So far we have learned OR and concatenation. Now it's the time to learn what is this Kleene closure and positive closure. Then we'll begin with the regular expression as soon as possible. Okay, A star. What is the meaning of A star? Actually, this is the simplest and best expression that represents Kleene closure of expression, right? You can't simplify further. But what is the meaning of this one? Anybody ask, sir, what is the language generated by this A star? That I can explain, like, you can say a power n such that n greater than or equal to 0. Or you can say epsilon a power 0, a power 1, a power 2, a power 3, and so on, which will give you meaning of epsilon a power 0, 1a, 2 a's in a sequence, 3 consecutive a's, and so on. Okay, so this is how you can understand with the language notation, but in the expression it is the simplest. Some people may try to write it a star is equal to epsilon plus a plus double a plus and so on, but this is not an expression. It is just only to understand what it is, right? Expression, it's not ending, right? Never ending, right? You are missing a lot of operators. Anyhow, this is a right way to understand, but not right way to express. Okay, A star means A plus. It means language generated by A plus. It means it is also a power n, but n begins from 1. That means at least one a should present, at least one time it should repeat. So what do you mean by this a power n such that n greater than or equal 1? A power 1 or a power 2 or a power 3 and so on, which will give you at least one a, or you may have any sequence of A's if you want it. That's the meaning of A power plus. Whenever you write A plus or positive closure of A, the equivalent language is going to represent this one. So understand, you write expression, but the meaning is here. As long as you don't convert your meaning into set, you might confuse a lot. That's what I'm trying to express here with the expressions, but also I'm explaining what is the meaning of that expression. So always come to this language to understand what is the equivalent expression, what is the meaning of expression. Okay, I hope you got this meaning. Minimum A, or you may have 2 A's, or you may have 3 A's, but writing this plus is not recommended as you don't have finite number of things to express. Okay, these are already a simplest one. Now you got to know what is a Kleene closure and what is the positive closure, right? Kleene closure means it starts with the power 0 and it is a power 0, power 1, power 2 and so on. A power plus means it starts with the power 1. So whenever you write something R star, you can understand which is same as R power greater than or equal 0. Whenever I write R plus, the minimum it should be beginning with 1 power. So this is how you interpret the Kleene closure of R and positive closure of R. Let's begin with some examples to understand both of them. The first one, suppose somebody said A followed by A star. What is the meaning of this? Can you simplify further? Yes, it is possible. Let me explain one regular expression when you write here. And to represent the same meaning, you can write infinite equivalent expression. That's why it's asked most of the times in the gate. You know, A star has infinite answers. But are you able to look at the 4 options which are given to you to find out which is equivalent to here? Because we'll have 4 options in the gate, and out of these 4, how many are equivalent to this? As you know, there are infinite equivalent answers are there. Fine. A star, what is the meaning of A star? Look at that. A is always there. A star, this A star can generate anything, but there is a dot, means compulsory these 2 are there. This will always give A, but what it gives? It can give epsilon or A or double A or triple A and so on, right? So when this A is taken with epsilon, what do you get? You get A epsilon, which is A. When you take this A followed by A, you get A followed by A, which is A square. And when you take A followed by double A, you will get A followed by double A, which is A power 3. And definitely A followed by triple A, because dot is there. That means you must take this A always. So A followed by A power 3, this is A power 3, right? A power 4. And what did you get? It's impossible to get epsilon. Epsilon is there only one side, but not both the sides. When you have both the sides, the result will become epsilon. See, epsilon will never come out, but minimum string is A, then followed by every string comes out. So whenever somebody thinking which is equal to A star, it is always wrong. Why? Because the A followed by A star will not be A star. A star will have an epsilon, but A star will not have. Why? Even though A star has an epsilon, but A star together you should think. When you think together, A epsilon become A, it's not epsilon. So it's very important, do you have an epsilon or not? Except that everything is there, but only epsilon is not there. Why is not there? Here epsilon is there, but this is not only one in this expression, because other always there. Other always there. That's why A dot epsilon will get as A in one choice. So now, what did you understand from A star? What do you get? What is this conclusion? A plus A power 2 plus A power 3 plus so on, it's equal to A plus. Yes or no? A plus. Not only this, if I say A star followed by A, again, this time first epsilon, then followed by A. And together it will get minimum A, minimum A. Then A square, how do you get? A followed by A square. A square followed by A cube. So here you will have again A plus. Now look at these 2 expressions. Even though you change the order A star A or A star, you get the same answer, at least one A in the language, right? Now this is the important point. Now let's come to the another conclusion. When I use the dot, you got this meaning, right? Now I'll go for A plus A star. Now something different. Both are not compulsory all the time. See, I want to generate this string. I can go to left of the plus or left to the plus, right to the plus. You can go any direction, right? If I go here, I can generate A. If I go here, I can generate A star. Now tell me, when you talk about the plus, it's nothing but union. When you talk about the dot, it's a followed by. That's why you are not able to generate epsilon from here. But can I generate epsilon from here? I can go this side or this side. If I go this side, I can get epsilon. That means A union A star. You can say A star. Why? Because they are already present in A star. So you can write A star. Now understand the difference. How did you get A star here? Here, how did you get A plus? This is equal to A plus, but A plus A star is A star. Where is the difference between these two? You need to analyze in the beginning only. Later on, you don't come to this, right? Later on, you will never come to this. These are the very basic questions. And this will, it's impossible, never generates epsilon. How did you know that? Because minimum string is A dot epsilon, minimum string is A. So which is equal to A plus, as you can generate A power 2, A power 3 and so on. But here, this is a plus. It's same as like, when I ask L of A plus A star, which is same as language generated by A union language generated by A star. Even though this gives A, but that's not compulsory when I take A. It's union. It's whatever A star generates. Whatever A star generates, right? Together what it generates? A star only. All the strings which are generated by A star will be here, right? So this is how you get it. A star means here you will have epsilon, you have A square and so on. Here only one doubt. So how did you get epsilon? Because this is R, you can go this side or this side simultaneously. So these two are independent expressions. You are doing the union. But when you go here, they are not independent. They are dependent one after other. That's why this epsilon cannot be pulled separately. But here this epsilon can be pulled. You can generate any point of time separately as a string. So this is the difference, and that is the reason this is equal to A star. This is just equal to A plus. Okay. Similarly, you can think about various expressions. I'll just write some of them. You just think about it. A star plus A star. Just think about it. A plus plus A plus. No confusion. I may write many things here, but don't confuse any of this. I'm repeating them. Okay. Few things only. As you know, there are many questions to solve here. These are the basics, then we'll begin with the questions after this. Okay, let's start with the first one. A star already generating every string over A, union with again A star, you will get the same, right? For this, no difficulty. R plus R, what it should be? R, there's no doubt about it, right? So whenever you have such situations, be careful. R plus R only. But only the thing is, when you are saying R dot R, you may get R, you may not get R. That depends on what is inside R. Remember, need not be equal to R. It could be R square, but R square might get R, might not get R. Depends on what R is. What R is. Suppose if I take R is epsilon dot epsilon, then epsilon square is again epsilon. If I take R is A dot A, which is A square but not equal to A. So understand what R is. If R is something which can give R again after R square, that would be special case. But here A star dot A star is what? A star square, let's say, correct? Because you are repeating twice. But when you are repeating A star again and again, so what do you get? Can I get epsilon from here? Yes, both are having epsilon, so that you can get epsilon. Can you get one A? Yes, first one I can put epsilon, second one I can put A. So epsilon dot A is what? A. So it's again A star. So now I need to explain how did you get A star? A star dot A star. Why did you get A star? Look at here. I will put epsilon all the time. Even though I have infinite choices, I put epsilon. Now I'll just take A star. One case I have A star. Other case, maybe this is A star. This is A plus. And this may be A square dot A star. It's something like A square dot A star. But whatever you get, all when you do the union, union. Combine them, you will get A star only, because A star will have all of them. A star is also part, and remaining all are already covered in A star. Together, it will become A star. I hope you got the point, right? It's just like union. When somebody is having all, union, some, right? The result has to be all, right? The same way, here A star is having all the strings. You're doing the union with the, some subsets only. So this is the important point for you. Now A star dot A star is A star. You can also write A star whole square, but don't write A square whole star. It's not just mathematics, right? So be careful. A star whole square is different from A square whole star. You may ask me, sir, can you explain a little bit about it? Okay. A square whole star. Why it's not equal to A star whole square? This is just now we understood A star dot A star, which is equal to what? A star, this one. And the first one, this A square whole star is, it's actually represent double A whole star. Means, which will generate epsilon when you put this double A power 0. And it can generate A square. How it can generate? When you put double A power 1, which is double A nothing but A square. Next, double A power 2 means 2 A's you write twice, you'll get A power 4, and you will basically get even number of A's. Even number of A's in every string that generated by the expression. Okay. Even number of A's, here this represent all A's. Okay, that's the main difference. Relation is like this expression, whatever it generates, the language generated by this expression will be strictly subset of the language generated by this one. So that subset relation exists. Come to the point. A star dot A, just now I explained A plus, A dot A star, A plus, A plus, A plus. Very interesting. Can I write A plus? Think about it. A plus dot A plus. Can I write A plus? If I write A plus, that means you're trying to say I can generate 1A. Can you generate 1A here? The minimum 1A here followed by minimum 1A. 1A followed by 1A. Is it 1A? No, right? 2 A's. So here it's impossible to say A plus. Okay, just conclusion. A plus dot A plus. Understand what is the minimum here? A. What is the minimum here? A. So what do you get when I concatenate? A square. Okay, later there are many choices. I can take A here. Here I can take A square, next minimum, to get A power 3. Or I can take A power 2 here, or A here. You will get the same A power 3. So like this, you can get every possible string after this. But here, 1A not exist here. Here, A not exist. In the whole expression I am talking about, not a part of the expression. Because it's a concatenation. In the part it may generate A, but altogether it can't generate A. Of course, epsilon impossible. As a minimum 1 length in each sub-expression. Fine. Now, what does this means? At least 2 A's. The meaning of this result is at least 2 A's you can generate from the expression. How do you represent this? 2 A's you can generate. Remaining any number of A's you can generate. Either you can write A star separately here, or you can write A plus. This A star you can also write A plus, or you can write A plus A, or what else you can write? A star double A. So many ways to represent, but each of this expression is trying to say I will generate at least 2 A's. But how do I generate? That depends on how do I express using Kleene closure and positive closure, right? So try to analyze A plus. How is it same as A plus, right? Try to understand this too. You'll get to know all the things are very easy. Fine. Just it is homework for you. Just try to cross check. Now with this, you got to know how to use our concatenation, Kleene closure and positive closure. But is this enough? No. Still there is a lot to know about regular expressions. Like first thing is, let me explain some properties before going to the questions. Okay. Here. See, we have plus, we have dot, and we have Kleene closure, that's star, another one is plus, right? Because there are two plus, right? Should know what are you trying to say. Or concatenation, Kleene star and Kleene plus. Now let's try to understand what did you learn. The unary operators are so simple. Only the definition could be difficult, but later properties are very easy. But R and concatenation properties are many. Many means because they are binary operators. When you are learning with the binary operators, you should know about properties like associativity, commutativity, and identity and dominator. There are many things to know about them. So the first two operators will have a lot of properties. Like, let me talk about some properties. Here, R and concatenation, let's talk about associativity. If you have studied in other subjects, it's fine, the same definition. Associativity. Plus and concatenation. Do they satisfy associativity? Yes, they satisfy associativity. What is the meaning of associativity? Let's talk about the plus. Like you have R1 plus R2 plus R3. Whether you take the left or right associativity, it should have the same meaning. Like I take R, this is a left associativity. Is it same as right associativity without changing the order of operands? This left plus you do first or right plus you do first. If you get the same meaning, the result, if you get the same, then we say that plus, that R operator satisfies associativity. So it satisfies. Similarly, concatenation also does the same. But when it comes to commutative, so it is important topic for you. You should know how it behaves. For R, you don't have any issue. Commutative means R1 plus R2. You can also write R2 plus R1 by switching left and right operands. We'll get the same meaning. Concatenation not same. See, if I have A dot B, if I change to B dot A, will not get the same meaning. That's why commutative will not be satisfied for concatenation. So even though it satisfies for R, but it will not for concatenation. So that's very important here. Similarly, you think about what is the identity for R. Identity in the sense, suppose you have R plus somebody you should write, so the result should be R. You know that pi acts as what? Identity. Pi acts as identity. You can also write pi plus R, which is equal to R. So here pi is an identity for R. For concatenation, R dot epsilon. So epsilon will act as identity. These are the three important properties. You know, there are so many other properties like distributive, dominator. There are so many. And if you are interested, you can learn about them. But this would be sufficient for the exam point of view. And associative, commutative, and identity. So identity exists for both the operators. Oh, these operators, these properties will not be there for Kleene star and Kleene plus, as they are unary operators, right? So all of them, you look at, you have the many operands with the same operator, but you can't have here. Remember, that's why these properties will not be reserved, will not be exist for this Kleene star and Kleene plus. That's why they are very simple. Once you learn the definition of these two, you don't need much to learn. But here, their definitions are so easy, but they are applied in different ways in different times. You should be having clarity. So with this, we got to know what are those operators and what are the properties of the operators and how you simplify when you have the multiple times the different kinds of operands. Now, now we'll start with some questions. Which of the following operators is not commutative? Very easy. Commutative means I told the R will check R1 plus R2, is it same as R2 plus R1? To understand it, just take any example or take understand the definitions. R1 union R2 has to be same as R2 union R1 when you convert into the languages. So it's going to satisfy what? Commutative. But we want not commutative. Okay? Concatenation. R1 dot R2. If two expressions are concatenated and if you switch left and right operand, like R2 dot R1 will not be equivalent sometimes may be equivalent, doesn't mean that it holds, right? If we say that it operator is commutative, all the time it should hold. When one time it is not holding, we say it's not commutative. So concatenation is in general not commutative. Fine. So B is not commutative. That's the right answer for this question. Okay. Sometimes you may be facing the question like, if R1 dot R2 is equal to, that could be possible sometimes. If R1 dot R2 is equal to R2 R1, then find the right choices for R1 and R2. Yes, it could be possible. Sometimes only, not all the times. Then what are the possibility? Then choose the right statement. Can you think about in which situations this R1 R2 is equal to R2 R1? There are many infinite cases might be there. Case 1, it could be possible when R1 is equal to R2. Then write it. If when R1 is equal to R2, R1 is equal to R1 R1, I can replace R2 with R1. Case 2, when it is possible, when suppose one of them is 5 empty, then whole result will be pi. Pi dot R2, R2 dot pi, both will give you pi. And case 3, when let's say R1 is equal to epsilon, what happens? Epsilon dot R2, R2 dot epsilon, whole result is what? R2. And it could be possible R2 is equal to epsilon also, any of this size. Likewise, there could be many possible cases where R1 R2 is equal to R2 R1, possible, but in general it need not be. Sometimes possible, sometimes not possible to be equal. Fine. This is about commutative for the concatenation operation. Let's begin with the first question. A plus B whole star is equivalent to, it's a very, very famous question in regular expressions. Okay, try to answer it. If you understood what is A plus B whole star, first time we are facing it, it's fine. If you come across this A plus B whole star, try to find out which is the right statement. The thing is, how many equivalent answers are there for A plus B whole star? Okay, infinite again. So why this infinite comes, right? If you want to express something, there are infinite ways possible, right? Every person could express the same thing in different way. The same way, whatever the language generated by this expression can be represented different ways. Even though they are expressions, but there are different ways. Fine. Will it generate the same as A plus B whole star? What is A plus B whole star? A plus B whole star means it has all the strings. You can't miss even one string. That's why we always talk about A plus B whole star. Is anybody generating all the strings? That is the right answer. If everybody generating all the strings, they're all right answers. Okay, the one of the option is all of the above. Could be possible all of the above, then think about it. I'll just show you A plus B whole star. What are the strings you will have? Epsilon, A, B, all right. You can't miss anybody. Yes or no? You already explained, whenever you write something like A comma B whole star, in the set we write A comma B whole star. In the expressions we write A plus B whole star. In the set we write comma here. Comma means in the expression it is a plus. Okay. Together we are writing whole star. So here in the expression we use a parenthesis to represent. But these two are equivalent notations, but two different topics. One is expression, other is set theory. Okay, which is same as like epsilon, A, B. One we use a set notation, other we don't use that. We can use here plus instead of comma here. Here we use plus instead of comma. That's fine. But understand they are all same here, equivalent. Okay. Now come to the point. Will it generate all? That is the difficulty here. Okay. Some people could not recognize is that every string generated. If you can make that difficulty into these strings, just try to find out the strings. Rather than looking at it, just try to find out the strings that can it derive. Okay, will it derive epsilon? Just think that way, that's enough. Will it generate epsilon? How? Just put a power 0. There are many ways, right? How do you generate epsilon? Using the first one, I can put power 0. Doesn't matter what is there inside. Or I can put power 1, but I go inside, I'll take a power 0. Or I'll put power 1, I can go inside, I'll put b power 0. Others I no need to go at all. Right. So there are many, even power 2 I can take. Power 2 means power 1, power 1. In the power 1 I can take a power 0, another one also a power 0. There are n number of ways, infinite ways I can generate epsilon from here. See that one string you can generate many ways. That is little difficulty in the beginning. Once you understand what is a plus b whole star, they are going to be easy, very slow. No, in the practice at the beginning, you need to practice why epsilon possible many ways, right? You might not realize if many ways possible, then which one should consider. Doesn't matter what you consider. Do you have epsilon or not? Is it having one way, 100 ways, 1000 ways, infinite ways? Nobody considers. That is the beauty of this expression. Think you have at least one way, that epsilon possible from here. Enough. Don't worry about all these things, useless for us. Okay? Nobody will ask how many ways. Okay? Really ask, then think about it. Now, is it possible one A? Because we need that, right? Because we want to check equivalence, right? So it has all. If not having all, we'll think about both valid and invalid. But now, A possible or not? See, A power, you put a 1 here, you put 1 here, that's enough. Take a power 1, go this side, no need to go both sides as it is a plus. And what about B? Take B power 1 and whole power 1, like whole power 1, so that you must go inside, and I'm taking B power 1. You have two choices, either you go this side or this side. I'm going this side to take a B. You have it. And similarly, do you have everything to generate? Yes. You can generate all. Double A you can generate. So think all possibilities. And why don't you think about, instead of these stars, just take power 1. It looks exactly same as above, right? That means you can take the choices of that only. That means A plus B whole star already here. But it has many other forms too, right? A power 2, B power 2, which can't generate beyond this, right? Okay, here. Oh, there's something different than the first one and second one, right? These two are similar so that you might interpret properly, but A star, B star. Many questions are there in the beginning when I'm learning TOC. How I get A here? Of course, could be easy. How I get B here? It could be easy. How I get BA? Some things could be difficult. So let me give you clarity. When you have A star, B star, whole star, what is your goal to generate? Only question is it generating all the strings? If it is really generating all the strings, then you should believe it has to be A plus B whole star, right? I'm just proving it. It generates, it will generate every string. Then you have to conclude. So my first question is, epsilon, will it generate or not? Of course, in the beginning, you can't say just generates. You should prove it. Okay, how do you prove it? So I'll just say that I will just take, doesn't matter what is there inside, I'll just take power 0. Remember, it's not only the one way. You can take power 1 also. You can take even power 1 also. But how do you get it? You put A power 0, B power 0. You can take power 2 also. But take the same A power 0, B power 0. There is infinite ways you have to generate epsilon from here only. Okay. Now, my question is next, how to generate A? I'll just show you one way, but don't believe that is only the way. You have other ways to do. 1A. I'm just showing one way how do you generate. How do you generate 1A? You must go inside at least one time. So I have taken one time only. A power 1, B power 0. Will it get A only? Look at that. A epsilon power 1 and A epsilon, which is A only, right? Obviously. Now, can it generate B? How do you prove it? I'm proving it. I'll go inside once. Of course, you can also go twice, but one is fine to prove it. A power 0, B power 1. That would be sufficient. And what about double A? Take A power 2. Go inside once. Take A power 2. Other is 0 anyhow. We don't want a B here. Okay, I'm just writing all the possibilities till you get a clarity. AB. How do you get AB? Because these are the strings generated by the given expression. I must follow my question to generate all the strings. AB, how do you generate? I want both of them as a power 1. Now I get AB. And how do you get a BA? So if you can understand this one, then everything will become clear. See, given form is having A's followed by B's. But look at the difference. A star, B star. If you have this, definitely impossible to generate BA. BA impossible because A is followed by B's. But what is the difference between these two? We have whole star, means after reading this, You can come back, but here you can't. But when you have A star, B star, whole star, you can read it and you can repeat and you can come back. You can repeat as many times you want. You can repeat. So that is the difference. In A star, B star, after A's only B comes. But when you have whole star, I can come back, I can do what I want. So now what happens here? Because of this whole star, I will estimate. First I need a B. For the B I take one time and A I will take one time. Totally 2 times I'm going inside. Actually power 2 I have separated. Power 2, power 1, power 1. Power 1 followed by power 1. First time I want a B. So I'll take a B power 1. I don't want A, so A power 0. So with this I got a B. And second time I go immediately, I want A, so I'll take A power 1, B power 0. That's it. Got that, right? B dot A. Right, 2 times I'm going inside. The first time I get a B, second time I get A. Similarly, you want any sequence. Let's say I want BBA, then BBA. 3 times I go inside. First time what do you want? B. Take a B. Second time B. Third time A. So you can go 3 times, or even you can generate by going 2 times. How? First time I go B power 2 also I can generate. So BBA. If I want to generate BBA, you can go 3 times or 2 times or even more if you want. But at least 2 times you should go. First time you can generate double B if you want, B square. Second time you just generate A power 1. But when you generate A, put B power 0. When you generate B's, put A power 0, because you are aiming for the first one symbol. Understand the technique what I am doing. My target is B followed by A. So when I generate a B, I put A power 0. When I generate A, I put B power 0, because that sequence is not recommended. Now I hope you got a clarity what I can generate from this expression. I can generate everything, right? Double B, how do you generate? B square here, A power 0, but go at least once. Okay, come to this. Now, should I believe it also doing the same, right? Epsilon, A, B, double A. But when I write directly, you may not believe it. That is the reason I'm going and explaining how do you generate. So it's your own work now. This one is also going to generate all the same things. So A, B, C, it's all of this. Okay, it's not only this expressions. I said at least 20 important expressions are there for the gate which are equivalent to this. But in general, infinite answers are there which are equivalent. Okay. A followed by A plus B whole star is equivalent. The previous one, A plus B whole star, means all strings. What is the meaning of this? It's in general, you can think about it. A followed by anything means all strings starts with A. If you try to understand the meaning, all strings starting with A. Any string which starts with A is possible here, right? Every string. Now you need to look at this. Could be, when you look at them, you don't understand are they doing right or not. But you should simplify it. Oh, I'm going to simplify first the given one. A followed by A plus B whole star. What is trying to generate? What is the minimum string? Epsilon or A? The A followed by epsilon, minimum string is A. Next minimum is, this always has A, but here you can take any string which is possible from here. So I'm taking first epsilon here. So A dot epsilon is A. Next, A followed by A. So here I have taken A. So A dot A is A. Can I get AB? So take whatever, A always there, followed by epsilon, followed by A, followed by B, then followed by double A, followed by AB. So A plus B whole star can generate anything like this. But any string you write, the first symbol is always A. All the strings starting with A are generated by this one. That's the meaning of the given expression. Now come to the options. I know, believe me, when I look at these expressions first time, I did get nothing during my BTech. Okay, so don't surprise by looking at these questions. The ultimate goal is, are you able to match the expressions? How do you match it? Not by looking at, not by simplifying it, just cross-checking both of them, right? So when you cross-check, you will get a conclusion correctly. Cross-check means what question is asking and what option is giving. So what question is asking is that I want these strings what option is giving, just you need to match. Okay. Okay, first one, what is the minimum string? If you can do this minimum string, nobody will stop to answer this question. Only the difficulty that you may face writing the strings in order according to lengthwise. If you can do that. So first, how do you do that? Think always like zero length first. Is there any zero length? No, because power 0 impossible, right? You inside epsilon is not there. Epsilon impossible, because if I go inside, a always comes. If I'm outside, there is no star. It's a plus. Okay, can you think about it? What is the minimum string you get? 1a, because take a power 1 and here put a b power 0 and take a. So a b power 1 whole power 1. So you got a b power 1 whole power, sorry, b power 0, sorry, whole power 1. A b power 0 whole power 1. What is it? A. Next, can I get a b? Think about it, because if you get a b, that's the wrong option, right? So you don't want a b. If it gives a b, leave it. Now, what is needed here? B, is it possible? No. Why? When I am trying to take a b, a always comes. So b is not possible. Very simple. So here in the order, just look at epsilon a b, like a plus b whole star strings. Just cross check them. You will get the right answer. Epsilon not possible, a possible, and b not possible, and double a you take twice, power 2, and take a b power 0. Yes, is possible. A b you take a b power 1 power 1. Yes, possible. B a, how do you get this b a? See, so far a b, all three are matching as per the order from the question, right? Next, B A, is it possible? Directly be impossible without A. So this is anyhow not possible. Double B impossible without A. And up to 2 length, both are matching. So there is 99% possibility both could be equivalent. But by looking at the options only, you have to answer it later. Okay, if none of this above is there, just go for 3 length and cross check 2. So up to 2 length, both are exactly matching, A and then double A, B. And later I did not check, because to save my time. Because in the exam, time is very important rather than finding the right answer. Sometimes some people find this right answer after 15 minutes, and some people will answer this within 1 or 2 minutes. So which is more important? Take less time and answer it correctly. If not, you can postpone it to the end, because you are spending more than 10 minutes for a question, means you are losing a lot of questions in the exam. Okay. Next, this one. What is the first string you can generate? Again, start from the beginning. Epsilon, A, B, and so on you have. This is generating epsilon. I don't want epsilon in the question. So epsilon is generated. So straight away you can say it is not equivalent. No need to go for any other string. So sometimes first time you try for the minimum string, you may get the answer that is not equivalent. So you ignore it. Not equivalent is very easy to answer. The next one. Anyhow, epsilon is not possible. That's correct. We don't want it. But single A, can you get it? Impossible. But we want A. So this one is not giving A. Why? Because whenever you want to take A, then B always there along with it. See that? You want A, but without B you can't be B followed by A star. So only A you can't take. When will you take? Suppose B plus A star is there. Oh, then only A you can take. But here dot is there, then only A you can't take, both you have to take. Right? So understand why you can't take only A. So here A not possible, but we want A. That is the reason C also we eliminate. Only A is left. That has to be correct, and verify if you want. You can understand. This is the one of the famous expression to say starts with A. Okay, I'll just show some of the expressions which could help you for future. Starts with A. What expression you have here? A, B star, whole plus. Okay, you should believe now that expression is also starts with A. Now, in case you want to have starts with B, slight change here, that's it. You just switch B here, A star, whole plus. Very simple expressions. Okay, there are many other equivalent answers. Okay, I'm not talking about, right? Similarly, you just think about ends with a. Okay, in case next question is there, you should answer very quickly. Now, when you have a starts with a, your focus is on a in the beginning. Now, ends with a, your focus is at the end. A and B is optional every time and repeat any number of times. Almost same, right? See that. Now, if it is ends with B, B is at the end and A could be repeated any number of times, but at least one string should end with B. So that's why we have a plus over. Now, these are the very famous and important expressions for the exam. You could remember sometimes you face it, but understand the how to place those A's. If you are starting with A, place A first. If you are starting with B, place B first. If you are ending with A, place A at the end. If you are ending with B, place B at the end within that positive closure. Within that positive closure. Okay, next question. Oh, now you may answer it very easily. Starting with B. So look at where is the B first? B is here. And don't believe that answer is right now. But identify B A star whole plus. Sometimes whole star will be there. So you should be very careful. That is the wrong answer because epsilon might be generated. Okay. So this is absolutely right answer. Sometimes could be possible. Other might be equivalent. You don't know, right? You never tried maybe. So now you should cross check. They might be wrong. You should eliminate it. Why this is not end with B? Because here only one A I can generate. So when one A I can generate, so how can be equivalent to starting with B? Sorry, starting with B, right? So this cannot be starting with B. This cannot be starting with B. So eliminate. Now here epsilon we can generate, but here epsilon not there. All the strings starting with B. So we eliminate it. Now I just told, right? This is only the equivalent to this one. So C is the right answer. But to confirm this, because here none of this might be there. If I have an option, let's say B whole star, whole star. If this is the C option, then definitely you can't choose a C also. Why? Here epsilon is coming out. But here that whole star is not there. Here plus is there. That is the reason this is the right answer for the given question. So sometimes you should be very careful while choosing the option, right? So C definitely the right answer. I've explained all the forms in the previous slide too. Okay. But when you have this, definitely this is not equivalent to the given one because of whole star only, because of this star. Okay. Yeah, now you choose it. I don't spend much time for you. Now ends with A. No guarantee of ends with A. So eliminate. Ends with A looks like, but here what is there? Star. That's why I deleted epsilon coming out. Right? You can't generate epsilon here. Now this one we require as ends with A and here positive closure is there. So positive closure and A should be there as ending with A and here B star should be there. So this will shoot our given expression. Fine. Let's move to the next one quickly. Okay. Find the equivalent regular expression for the language which has even length strings. W belongs to A comma B whole star and every string is even length. What do you mean by even length? Whenever I say length of the string is even, what could be even length? Suppose I have epsilon, A, B, double A. These are the strings in the particular order, right? Who are going to be even length? Epsilon, 0 length. This is right. Length I am talking about. 1 length, we don't want. These are all 2 length. Yes, we want them. So this kind of strings, 0 length, 2 length, 4 length, 6, 8, and so on, those strings should be there in the language. I hope you got the problem first. The language which has all the even length strings. Language which has all even length strings. Those are nothing but epsilon, double A, AB, BA, BB, and so on. So I'm writing those strings here. Epsilon, AA, AB. Writing all those even length strings are difficult in listing format. So we have written a conditional set format, right? We have mentioned all the conditions in the set and that will give you all the strings which are having even length. So now we got a clarity. We have a language which generates all even length strings and we have an expression. We want an expression for that. Okay, you may have, may not have, but you should understand what each one does. Okay, so we want equivalent. Remember, we want equivalent that should only generate, and it should generate all even length strings. Remember, two words are very important when somebody is saying equivalent or denotes. Remember, it should generate all what you need, and it should generate only what you need. It can't generate even one extra, one less. Okay, a plus b whole star, you know already it generates everything including one length, so that we don't want, right? So what is the relation? It is a superset. It's not equivalent, it is a superset, so definitely we don't choose it. Okay, and oh, what is this? And how do you understand this form especially? Now remember, when I write epsilon, what is meaning? The zero length. When I write a or b, oh, one length. Now you may have a doubt, sir, only when I write a is also one length, and only when I write b is also one length, then a plus b also one length. What is the difference between these three? When I write a, one length, but not all one length, it's only a. When I write a b, it is also one length, but not all one length. But when I write a plus b, it represents all one length. You can't miss even one length. That is the difference. Even though a is one length, but it can't generate a b. It's a specific one length. Remember, specific one length. So now this will generate one length, this will generate one length, and overall it will generate just two length. This can be written as a plus b power 2. Means it is generating only this two length. It is not generating 0 length, 4 length, 6 length. So this is very specific case, and it's obviously same as a C. B and C both are same. There is no difference, right? Correct? So these two are generating only two length, but we want all even length. So B and C are also not correct. It's not equivalent. Even though it is even length, 2 is even length, but it's not all even lengths. We want equivalent. Remember the word. So here we don't have an expression that generates all even length. So we choose option D. None of this. What is the actual expression now? You may get it out. So how do I write an expression that generates all even length strings? So let's do that. Now answer is here only. Here also there. See, if you want to generate all even length, okay, just let me write here. What is even length? 0, 2, 4, 6, 8, and so on, right? How do you do that basically? For this, just you need to have some variable, right? Somebody should say 2k, where k greater than or equal to 0. So if you have a 2 length, repeat any number of times, you should get even length. So 2 0 0, 2 1 2, 2 2s 4, 2 3s. That means if you should know 2 length. So already you know the 2 length, right? A plus b whole square is a 2 length. This 2 length you repeat as many times you want, you will get even length. C star means any number of times you repeat. 0 power 0 means you will get epsilon. Power 1 means you will get all the 2 length. Here you put a 2, then this 2 length you repeat twice, you will get 4 length. So this form you will have all even length. So this is the right expression for this answer. Okay, so a plus b whole square whole star. Maybe you can simplify this if you want it. There is another way to write, like double a or ab or ba or double b whole star, and you will get all the even length strings. You will get all the even length strings. You can represent any form. Okay, next one, all odd length strings. Oh, what's the difference between even and odd? For even, you just do one more length extra concatenation, you will get odd length. Okay, in mathematics, even plus 1 is always odd. Okay, so this is going to generate all. We don't want all. Here, not, at least one, because this a plus b is one length. This will be any length. Overall, when you do 1 followed by any, will be at least 1. So here at least one length comes here. At least one length. I'll just represent length of w greater than or equal to 1. All means length of w greater than or equal to 0. And this one is just now discussed, right? It's even length. Oh, so not even length. At least 2 length. Sorry, it's not whole star. This is equal to 2. This is greater than or equal to 0. What do you get? Length of W greater than or equal to 2. From 2 onwards, 3 length extra 1 you take. Already 2 is there. If you take power 1, you will get a 3 length. If you take power 2 here, you'll get 2, 2, 4. And from 2 onwards, every length can be generated here. Then what is the question? You want odd length. How to do that? Even length, already you have it. Take that. What is even length? A plus B over 2. That's 2 length. You repeat any number of times. This is even. Now, one length you concatenate after or before. You get odd length. So already even length. Epsilon is generating, but odd length will not have an epsilon. So you take just A plus B at the end. Or you can take A plus B whole square whole star. You can take one length before also. Will get the same meaning. You'll get the same meaning. Both will generate odd lengths, all odd lengths. Now you just try it. What do you mean by odd length? Odd length is first A or B. Then 3 length. Oh, 3 length, there are many strings. The writing will take time. So I'll just keep like this. Okay. You guarantee that A comma B. Here put power 0, you're already there. And 3 length, how do you get? Take a power 1 here. So 2 length followed by 1 length, you'll get all the 3 length. Similarly here also. Okay, once you have even length, odd length is also almost same, but add extra 1 length to the even length, you will get odd length. Okay. Whenever you see the difficulty with the expression, just convert into very nice form. Like, you know, when somebody says like this, you know, X is nothing but A or B. Assume this, then how it looks like? X square whole star. How simple it is to understand, right? The X is already, I know, 1 length. So X followed by X square whole star. This looks so nice, right? And when the language is over 1 symbol, we always write this way. But when the language is more than 1 symbol, you need to represent properly. Okay, but same one you can denote for the 2 symbols also, but assume X is equal to A plus B, then you can write this way. Okay. We have the next question, which is having a language starting with A and ending with B. See, W is anything, so starting with A, ending with B. Here, important concept is you should know what actually language has. The language has a strings starting with A, ending with B. Then expression would become very easy, right? In these 4 or 3 options, which of them is doing that starting with A, ending with B? Is only having starting with A. There is no restriction on ending. So this is the starting with A problem. You may just represent as A followed by something. That's it. And this one, yes, it has A and anything definitely ends with B. This is what we are looking at. And this one, anything is there followed by B. This is for ending with B. In this, there are 3 problems: starting with A, ending with B, and ending with B. The question is very clear: starting with A, ending with B. So we'll choose option B. Option B. Starting with A, ending with B. So this is how you analyze. See how much time it took once you know about the expressions. Hardly it will take sometimes even seconds, 5 seconds, 10 seconds. But it all depends on the problem, right? How good at your practice, how good at understanding, and how you are practiced, and how many questions are practiced, all matters at the end. Next, sometimes even though you practiced a lot and you may come with the wrong options, or you come with the right options, but that's not enough. See, if this is MSK question and you might be worried about how many answers are correct, is it all or 1 or 2? So here the challenging comes. So I'm saying it is MSQ, and it's your job is to identify how many equivalent answers are there. So I may not be, 100% explaining correctly right now, because you need a DFA to understand this behavior. When you construct DFA for this, deterministic motion for that, you will get to know why we are writing this. So spending much time on this question right now is not recommended, but I'll come to this question again. But let me discuss in my way first. Okay, what is the language? Well, language is, it is having many strings, all strings, where contains AB, and before after anything, W1 and W2. Okay, you may have a problem. Why don't you write, sir, W, AB, W, such that W belongs to A comma B whole star? Anybody? Is this right way to write? No. If you do this, you are saying whatever is there, it is also here. But we don't. Containing AB before, after anything, not the same thing. Before AB, suppose triple A is there. After AB also triple A, no need to be. So that's why we require W1, W2. The question is very clear. Containing AB. Containing AB as a substring. Okay, that's why we need to write two different variables to represent before AB, after AB. Okay, now in this, when you look at the first option, oh, you are great. AB is there and anything before and after also anything, definitely A is correct. No doubt A is correct. That doesn't mean that others are wrong, right? You should know about the properties of these expressions too. Okay, what kind of property you look now? You know, containing AB. So now let's behave it like containing AB is there. If you want to see the first time AB, here no need to be there. If there are two ABs inside the string, this AB could represent any AB, right? But there are some other ways to represent AB. Suppose first time AB comes, first time. Before that, what possible sequence may come that never contain AB? Because you are looking for AB, right? After that, anything is fine. After that, any. But this is the first time AB. First time AB appeared. Then what is the possible sequence you have here? Can I will never have AB here, right? So can I have any number of A's? Yes, you can have any number of A's. Any number of A's. Can I have any number of B's? But not after. Before that, any number of B's I can have. Still I don't have what? AB. So there are two choices. B and A's, any can come, but B is followed by A's. So here something like B star, A star can happen before having AB. Before first AB. Once you have AB, doesn't matter. So this kind of form can also generate the same language. That is very important. See, B's, till A is not appeared from this AB. So we are waiting for that. Once A's comes, any number of A's doesn't matter, but followed by B will give you containing AB. So one of the difficult, only when you don't know DFA. When you know the DFA, because to design a DFA, you have to think this way. There is no other way. There is no other way that you can construct DFA for this. Okay. Now, if you want to construct DFA directly, you have to think this way, right? But there is a technique. We have techniques to construct the DFA by taking the minimum string here. Okay. Now look at this. Here, A star A. Oh, no need to write in this way. Look at that. I'm just writing here B star A star AB followed by A plus B. This is the expression I have explained. But you can, these two are together, right? You can also replace with A plus, right? B star A plus. This is another way you can write. Or you may write B star A star. You can also switch like A star. A star A star. You can switch any because both are same. See that how many ways you can write. These two are actually same. A star you can write, A star A you can write. You will get the same answer, right? These two are also equivalent. And again have a doubt. How this is written? How can I understand this? Sometimes you don't need too much because already the question is very clear. Look at the option A. Look at the option A. This one is looking like ends with A. This one, it's looking like starts with B. Just this expression, this one, somebody has written some other way. Like this ends with A and this looks like start. Of course, don't say that. But it is expression, right? This one I can replace with this form because ends with A form I can replace with this expression. I just explained ends with A and starts with B how to write it. This another form starts with B and just replaced it. This one replaced with B star A whole plus and this one replaced with B a whole star whole plus. That's it. This is also going to be equivalent. The only thing is we must have much practice to know about all the different forms and which are important. As I said, everything is not important in the world, but which are minimal and required for the exam, I have covered in the options itself. Okay, these are created by me, But these options were already asked in the gate, like what is this, what is this. In future they might give this and they put this in the options. You should think about their way. Okay, fine. So all the options are correct. All the options are giving somehow containing AB as a substring, containing AB as a substring. Number of A's is even and no condition over the B. Look at that. I want all the strings which are over A's and B's, and number of A's is even. Here, number of B's, we don't have any restriction. Now look at all the options, think about what each one is doing. Now you are focused on number of A's is even, right? Suppose sigma is only over A instead of A comma B, answer straight away, that is A's is even, right? Whole star, whole star. But here B is there, A comma B, right? So now you should think some other way. Now what way it can solve? Multiple answers are there, and no doubt it is important for exam and asked multiple times so far. Why? Because very easy to confuse you with a lot of variations. Okay, first I'll explain which are not correct so that you can conclude what is left at the end. Why this option A is not correct? You just think about it. First is number of A's is even. And where is the condition? Here 1A, here second A, and third A I can generate from anywhere. That means 3A's also I can generate from here, right? 1A, A, remaining I put epsilon. So this is definitely wrong. It cannot guarantee even number of A's. Maybe it will generate all even A's, but also it will generate not even A's too. This one, exactly 2 A's. My question is not about exactly 2 A's, it's exactly even A's. So this will generate exactly 2 A's. What is this? How do you write condition? Here instead of even, if you have equal to 2, definitely this could be the right answer. Then what is this? Sir, what is the right answer for this? I have 2 A's and remaining places anything is there. This will guarantee number of A's will be at least 2. Look at that. The question is, if it is greater than or equal to 2, you should choose option A. If the number of A's equal to 2, then you should choose option B. What is option C? Option C is somewhat difficult to say. Why? Because the option C and D almost same, but here only B's you can generate in this option D. Here only B's you can't generate, because if you go inside, when you take a B, A also comes. So in between these two, whenever you want A's is even, definitely AA whole star could generate even A's, but B's can come any point of time. B's can come here, any number of B's. B's can come here, B's can come here, but that's not enough. B's can come here also or here also. This is actual answer for the question, but this is not given anywhere. And look at this, here only B's you can't generate, because 0 number of A's also right answer, but here epsilon you can generate. Here what is not possible? Epsilon okay, but B you can't generate, but B is having even number of A's. 0 A's means even, right? But here impossible. So to cover up that, you need additional B star, or keep the B star here or here, answer will be sufficient. So you can choose this answer, or you can choose only B star here, and you can try as homework. You don't need these 2 B stars, you can keep only one, that's fine, or you can keep only that B star, that is also fine. That's why this question is very, very important for the exam point of view. How do you write this many ways to say the same thing? And otherwise, why do you write B star here or there? Keep outside also, that would be fine. Still the language you get same. Additionally, B star. How many other? I'm not writing here. If I try to discuss this, I may take half an hour sometimes for only this problem, right? As it crash course, so you have to understand why this many expressions are there to say this is right language, or all these expressions are equivalent to this language. Okay, so now D is the right answer, and B, C are also wrong. But C is only the one thing which is missing. Only B's I'm not able to generate. That is the reason I'm going for the option D, right? Option C is there, option D, none of this there. You must go to none of this because this can't generate all strings that are having even number of A's. Okay. Keep this as very important and practice all these expressions, and these are all our same, and that is solving the given question only. Okay. Which of the following regular expression identities true? It was the pre-by-q, and you should know what is well-formed formula. See here, somebody has written some different way. R star, you know, R star you can write like this, or R star you can write like this. What is this? R star. It's not well-formed at all. So ignore this option. This never be correct because that's not well-formed. As you know, operand you can take parenthesis, but if you put a star for the operator, then whom you are applying, right? So operator should be applied for operands. When you close this operator, you're not mentioning any operand for it. It's not well formed, first thing, so don't think about it. It's always wrong. Okay, next, true, we want to choose true, right? You already know about it. Is this true? As you know, R star, S star, whole star, that is equivalent to. But what is given in the option? We have tried A star, B star, right? In place of AB, we have RS, that's it. Here star is missing. And are they equivalent? No. How do you know they are not equivalent? Very simple question. From here, SR you can't generate. But from here, I can generate SR. That's all enough. Why they are not equivalent? If they are equivalent, they should generate same set. What about this one? This one, R plus S whole star equivalent to, if you have R star plus S star whole star, then these two will be equivalent. We have tried in the previous questions. A star plus B star whole star, there was a first option for this question, right? This was the question, this was the first option. Fine. Now here, what is missing? You can see from here, RS I can generate. How? I can repeat twice. First time I take R, second time S. But from this, RS is not possible because only R or only S. How can I do RS together? Not possible. Okay, this one is very simple. Again, here RS you can generate, but here RS you can't generate. That's why which is equivalent here, you can see. Anybody is true here? No one is true? Oh, that's great. All are wrong. There's a possibility to make it equal when either you put whole star here, or you put here already parenthesis there. Maybe in the actual gate question you might have a star here, so this could be possible right answer in the gate question. But here, you know, I slightly change the question, so here all of them are wrong. All of them are wrong. Such questions are not possible in the exam. At least one option should be correct. So in case this one, if it is given whole star, then definitely this option could be correct. Okay, try to look at the possibilities. Oh, next question. Which two of the following four expressions are equivalent? So we have four expressions here, and which two are equivalent? Now, for simplicity, let's try to understand very quickly. And what is the meaning of this? Okay, just write the star above, 0, 0 star, epsilon plus 0. So can you simplify very quickly? Yes, just distribute it properly. 0, 0 whole star, epsilon plus, and then for this you apply 0, 0 whole star. You got distributive, right? You applied to. Now this one is 0, 0 whole star plus this one is 0, 0 whole star 0. These are the very simple things, you know. This is having all even zeros. This is having all odd zeros. When you have union, even zeros, union, odd zeros, you will get all, right? All zeros you have. You did not miss anybody. You want epsilon, you have here. You want 0, you have here. You want double 0, you have here. Triple 0, 4 zeros, 5 zeros, 6 zeros. You have covered all the strings over the zeros. That's all zeros, which can be written as equal to 0 star. How beautiful it is. Now, when I write this, you got to know that yes, 1 and 3 definitely equivalent. So just cross check others. The 2 is even zeros, 4 is odd zeros. So 1 and 3, 1 and 3, where is it? This is the right answer. Okay. Which one of the following regular expressions denote the set of all strings not containing 100 as substring? Really, I'm saying directly identifying such questions not easy. Okay, I always say truth that as per my knowledge, whenever it is easy, I say easy. Whenever it's difficult, I try to say it, because you can challenge yourself to learn much. This kind of questions might waste our time, so you should have well strategy to practice. Why it's not easy to answer? Because not containing 100 is different from containing 100. Containing 100, you can say 100 before after anything, 1 plus 0 star before after, that would be fine. When I say not containing 100, you can practice a lot how to write that expression, or you try to eliminate from the options. That would be sufficient. Always we choose in the regular expressions elimination technique. So now let's try. What is the question? In the language, not containing 100 means whoever not contains 100, that should be there in the language. Let's say epsilon. Is it containing 100? No, that is a valid string. 0, 1, 0, 0, up to 2 length, everybody will not have. Yes or no? Up to here, there is no 100, no problem. But after that, whenever you see 100 as a part of the string, should not be there. 000, no need, right? Just try to understand what I'm saying, right? A 100 you should not write. So 101, 110, 111, and so on. In 4 length, never try to have a string 100 as a substring. If any string has 100, don't keep in the language. Now all the strings will never have 100, right? Now come to the options. You don't need all this. Just for explanation, for understanding the problem, I keep on writing it. But actually it can be answered within a minute. Sometimes even with few seconds also you can answer it. Okay, let me explain my way. Option A. Is it not containing 100? Sometimes you need to think two ways. Is it containing 100? Eliminate. Is it containing 100? Eliminate. 100, see here. Do you have a 100? Try. 1, 0, 0. You can have it, right? This everything is possible here, right? Everything is possible. So 100 here. But we don't want it. We don't want it. So option A, eliminated. See, this is what I'm saying. You apply the elimination technique when you are not able to interpret directly. Now look at this. Is it containing every string who is not having 100? See, there are two ways to think about. Definitely you look at it, there is no 100. There is no 100. You have it, right? Oh, here 100, 100. Okay, let me come to this later. You have 100, right? Definitely it's a wrong string. But no need to think about that way. See, my language has epsilon. This is not giving epsilon. Enough. Right? Sometimes you look at your problem. Whatever I have, I should have from the options to say they are equivalent. Now epsilon is there in my language, and the option also should generate the whatever I have. Epsilon I have, but option is not having epsilon, so delete it. That's one way. Another way, 100 it's generating, but I don't want it. Here see 100 it's generating here. Okay, next option B is deleted. Option C. Here when you look at, actually I was trying to explain B, but now I'll explain. Definitely when you look at here, 100 impossible. That doesn't mean that both are same. Right. I'm trying to say again, it will never have 100, but it is not equivalent to the given question. It is a subset. But I want all these strings, not just few strings here. What I'm trying to say, I want every string in the world who is not having 100. Is that clear? But this is not giving all the strings, is giving only some strings. That is the reason. How do you know that? See here, just look at our epsilon. I want epsilon, but this is not giving an epsilon, even though it is giving some strings only. It's there in the language, but not all the strings. Okay, all the strings present somewhere here, but I want whole this language, right? So option C eliminated. Only the reason is C is a subset of our language, not equal to our language. Okay, next option D. Now look at this, epsilon was not giving, right? Here epsilon possible, look at that matching. Next 0 possible here, 1 possible here, 0 0 you can take from here itself by putting epsilon the second one, 0 0 0 1 0 here and 1 here, 1 0 you can generate from here, 1 0 1 1 you can repeat this twice, and 0 0 0, yes, you can generate 0 0 0 here itself. So look at, are you getting everyone? 0 0 and 1 here. Okay, try to understand how do you get each string. And 0 1 0 0 1 0 here, 0 1 0, and then 0 1 1 1 0 here and 2 1s here, and similarly 1 0 1 you have 1 0 and then 1, and 1 1 0, so you have 1 here and then 1 0 you can get here, and then 1 1 you can get. But why you don't get 1 0 0 here? You try here. Why I'm not getting this 1 0 0? I don't want it, right? I'm not getting 2. See, 1 here, if I take 0, other 0 impossible here, because you can't come to this. If you don't have whole star here, if you have whole star you can come back and you can get this 0, but you don't have it. Once you have 1 0, other 0 immediately not possible, right? You can come back, but 1 0 1 0 comes, but not 1 0 0. So here, except 1 0 0, except the strings who are having 1 0 0, all the strings are possible here. So this is a very well known expression for the language that is not having 1 0 0 as a substring in every string. Okay, so this is a very well known expression. Okay, look at that. When we want to eliminate, definitely you should have the technique. What are the minimum strings who are present in the language, who are not present in the language? That would be sufficient to eliminate it. Maybe I have taken a lot of strings to make you to understand, but this could be answered within a minute if you know the technique. Okay. Okay, very easy question again. If the regular set A is represented by A is equal 0 1 plus 1 whole star, B is represented 0 1 whole star 1 star. It's very simple, like you may assume just x is 0 1, y is 1. So A looks like x plus y whole star, B looks like x star y star whole star. Very simple. Okay, x y you may assume A B, that you already solved it. We know all these two are already equivalent, right? These two are already equivalent, so you can simply go for option D. When you are able to interpret it properly, this can be done quickly. When you are not able to do, just try to check, are they doing the same things? Okay. Of course, these things are wrong. Only the reason is, if instead of this A subset B, if the right A subset are equal to B, this is right, and B subset or A, it is also right, and A equal to B, it is also right. But here they have mentioned clearly strictly subset. That's why we don't choose it. Okay. Fine. Again, we have similar question, which of the following is true? You know, that's what the question is about. S is mentioned A plus B. Once you know about A plus B whole star, many things look so easy. And I don't need to say, are they equivalent or not? What is the relation between these two? I just told S is equal to T, because these two are going to generate the same set of strings. And when these two are equal, you can write S subset are equal to T, or S superset are equal to T. And these options are obviously true. And what else you can say? S intersection T has to be S or has to be T, because both are same actually, right? Now here strictly subset wrong, and equal to correct, and here equal to pi. Pi is means there is no common string, but we know S and T are same, so S intersection T has to be S or has to be T. Definitely it has to be. You can't say this equal to empty, right? How easy now to compare the two languages? Okay, can you do it now? I just explained it in the beginning, but you know, we are doing continuously. Definitely you might be missed somewhere here, somewhere this expression. Which one is equivalent to? There are so many, right? Think about. It's one of the again important form for 0 plus 1 whole star. 0 plus 1 whole star or a plus b whole star. You have a lot of forms. This form you did not see so far, but if you see somewhere one of the option you might have been seen. Now let me explain again why this is equivalent to 0 star 1 0 star whole star. Okay, think about it. Various ways to explain. I explained some time back 1 0 star whole plus, but that is starting with 1. Now if it is not starting with 1, it could start with 0, so 0 star, and this may or may not present, so star. The small changes to that expression could make starts with 0, or to generate epsilon you need to have the whole star here somehow. So there is a form, and many forms are there here. Okay, this is equivalent to 0 plus 1 whole star. Why? Epsilon can you generate? Yes. How? 0 power 0 and this power 0, you will have epsilon. Can you have 0? Yes, here you have 0 power 1, put power 0. And whenever a string starts with 0, take this 0 into consideration. Whenever it starts with 1, don't take this, and you will have everything here. Okay, remember everything here. So it's very simple. Once you started, you go inside by ignoring this, by putting power 0. And whenever the string starts with 0, then take this 0, other 0 you can get from here, and 0 1, take 1 0, another one from here, and so on. Everything is possible from this expression. I'm saying when the string starts with 0, take this 0 into consideration to generate the first 0. And whenever the string starts with 1, take power 0 and starts with 1. Already it is possible to generate it from here, because whole plus we have seen. Now it is just whole star, additional epsilon is there. Okay, now come to this one. Which one can generate all? Okay, now look at here. 1 star 0. If you don't have this, and that's almost generating ends with 0, all strings, not almost all, but additionally epsilon. Additionally, let me explain that to 1 star 0 whole plus. It ends with 0, right? It's a form for ends with 0. Now what do you have? Additionally epsilon. Whole star means power 0 is added. Now here ends with 0 or epsilon, and this one will guarantee ends with 1 or epsilon. So somehow here ends with 0 and ends with 1, all the strings are covered. So definitely this is equivalent to 0 plus 1 whole star. And really you want to know much, just try to generate one string, every string. You will see every string which is present in 0 plus 1 whole star. And now elimination is so easy here again, rather than finding the right answer. But I could explain much about it. But as you know, you need to cover many things again. Now 0 plus 1 0 whole star. What is missing here? Can you find out? Can you generate epsilon? Yes. Can you generate 0? Yes. Can you generate 1? No. That's enough. Why it's not equivalent to 0 plus 1 whole star? See here, can you generate 1 here? Yes. How? 1 here, 0 power 0, whole power 1, and 0 power 0. So this could give you 1. But here 1 impossible. When you take 1, 0 also comes. Here 1 is not possible. Very straight away. So be eliminated. And here epsilon is not there, but we need epsilon. Epsilon is possible in the given expression, right? C is wrong. A is equivalent. So here the expression that ends with a 0, right? Ends with 0. The whole plus, now you have whole star and 1 star. You want to write many other expressions? Yes, you can write lot other. But I'll just give you a hint. When you take starts with 1 and you consider 0 star. When you take starts with 0 here, if you put 0 here, I'll write here 0 1 star whole star. Whole plus is there, actually whole star now to have an epsilon. But here you just write 1 star. You try on your own. Will it give all the strings over 0 plus 1 whole star? Not only this. This ends with 0 concept, right? Now I'll keep ends with 1 concept. 0 star 1. Whole plus was there, actually ends with 1. We have whole star. Ends with 1. If not ends with 1, ends with 0, 0 star. Look at all these 4 expressions and try to do on your own. This should generate 0 plus 1 whole star. If not, comment below the video. And if you miss any string, how to generate from that, I will help you. So you keep on trying it. You keep on trying it. There are various expressions which are equivalent to 0 plus 1 whole star, a plus b whole star, and all of them are very, very important. In case if you would want to know about various expressions, let me write many forms now. 0 plus 1 whole star, or you can take a plus b whole star. Both are same, right? One thing you know, you may are a plus b plus epsilon whole plus. Very important form equivalent to this one, because epsilon outside you can generate, now here inside. That's all. Everything is same. And you can write a star b star whole star. And I'm just writing rather than explaining all these things. Please work on each one. Whole plus and whole star, even though looks different, but generate the same set. And each one equally important for you. Please work on each expression to understand. Very, very important expressions only I'm writing here. The many things I may miss, you see directly them in the gate questions, you can easily identify it later on. A star plus b star whole star. Did I miss anything else which are important so far? Okay, just now we have seen, right? Starts with A is there, suppose. So you want starts with B, then B star you should have. Suppose starts with B you have here, and starts with A you should have A star. Suppose ends with A, then B star A whole star. If you want to end with B, you need to have this one, ends with B. So there is a concept that I'm following which will help you when you practice. So when this is covering ends with A, then to cover ends with B, you should keep the star and you should have here B star. Similarly, ends with B is here, so ends with A, to make it A star I kept it. Similarly, starts with B I took first, then to have the starts with A star I have written. So there is a logic why I'm writing this to make A plus B whole star. All these expressions are really important for exam point of view. Okay, in case if you are able to remember all this easily, that would be fantastic. In case you're still having any difficulty, you can have a discussion. You will learn a lot from this expressions. Which of the following statements is true about the regular expression 0 1 star 0? Okay, I was talking about the language, right? Or set. Is it finite language or infinite language? It's definitely going to represent infinite set. Correct? So now look at which is not saying infinite set. Finite set, infinite set, finite set, infinite set. It's infinite set. So whoever saying finite set, eliminate it first, because not a finite set. So now it is infinite set, but having what strings? Is it having finite strings? Is it having infinite strings? I told language never contain infinite type strings. It will only contain every string we use finite. Now look at when you write here, minimum string is 00. Next string is what? 0 1 0, 0 1 1 0, 0 1 1 0, and so on. Every string is finite. Can you see that? Such finite strings are infinite, but every string is finite. So it is infinite set having finite strings. Infinite set means already infinite number of strings. I have infinite number of strings, but every string is finite only. You can see here how many strings are there. This is infinite set, but each string is what? Finite string. This is also finite string. This is also finite string. So every string is finite, but those strings are considered infinite times, so we call it as infinite set. It is infinite set, it means there are infinite number of strings, but every string is finite type. So this option B is right and D is definitely wrong. In case if you want an example for each one, let's see. It represents a finite set of finite strings. Example. Okay, if you want an expression, the expression I'll take. Finite set, finite strings. Let me take 0 1, right? 00 1 1. I have how many strings? 2. Each string finite. That means Equivalently, the language is 00, 111. So 2 strings, finite language. How many strings? 2 strings, each one is a finite type. This is the finite, this is also finite. And option C, finite set but infinite strings. Oh, we can't write, but still I'm writing just to explain. For this, finite set, okay, I'll keep only 2, but having infinite type strings like 0, 1, triple dot. Oh, one string itself infinite. Another 1, 1, 1, triple dot. That means, see here, the string I can't complete it because the string is already infinite. When the string is infinite, how can you complete one string? Very difficult. What is there after to know? You know, at least in real number, you have a bar to represent if it is repetitive. Here we are not denoting any such things because they are not used in computation. Another one, infinite set of infinite strings. Oh, what is it? See, 0, 1, 0, 1, 3 dots. 1, 1, 1, 3 dots. 0, 0, 0, 3 dots. 0, 1, 1, 0, 1, 1, 3 dots. Likewise, you have infinite. Every string is infinite and such strings are infinite. Okay. In general, I already told you set can be infinite, but string has to be finite. Every string has to be finite in the computation. You know, it was a very beautiful question in the exam so far. Okay. Which one of the following languages over the alphabet is described by the regular expression? Identify quickly. I told you right already, no need to spend much time. 1 0 compulsory, other 0 compulsory, which will give you at least 2 zeros. 2 zeros guaranteed, third, fourth, anything you want you can cover from other places. So at least 2 zeros. At least 2 zeros. Okay. Where is that? Containing at most, containing at least this one. Okay. In case you want to know all the expressions, set of all strings containing the substring 0 0. Can you write it quickly? 0 0 before after anything, right? 0 plus 1 whole star, 0 plus 1 whole star. When I write capital X, understand it is 0 plus 1 whole star. Containing at most 2 zeros. At most. You know, you should know how to write it. 0 plus epsilon means at most 1 0. So I'm going to keep at most 1 0 here, another 0 here, at most 1 0. So 1 can come any place. So I may write 1 star here, 1 star here, 1 star here. This will guarantee no 0 if you want to take epsilon. If you want 1 0, any one of them take 1 0, other is epsilon. You want 2 zeros, take both of them are zeros. You want 3 zeros, impossible here because maximum 1 0, maximum 1 0, it will guarantee at most 2 zeros. Okay. Containing at least 2 zeros is already covered. All strings that begin and end with either 0 or 1. So this question, you may think about it, begin with either 0 or 1 and end with either 0 or 1. Which is, everything is possible, right? Is there any condition here? Begin and end with either 0 or 1. Anything is possible, right? Except epsilon, everything is possible here. Like 0 plus 1 whole plus, if you take, it will begin with 0 or 1 or end with 0 or 1, always. So except epsilon, everything is here. Fine, 0 plus 1 whole plus. Okay, next topic is finite automata. In previous topic, regular expressions, I think almost all important questions are covered. Really, now you can go for the gate questions and try to practice it because I've taken a lot of gate questions and a lot of new questions and a lot of questions which will help you to understand all the concepts. Now, I hope you have understood various types of regular expressions. Now, with this, you will get an idea what is a regular language. That means when I say the language is starting with A, oh, I have a regular expression, so it is a regular language. You should have that kind of opinion now. What is a regular language? Have you understood them? Have you seen them? Right? Have you written them? Yes, so many. But what you have not understood so far is what is non-regular language. We can come up them after completing finite automata. What is non-regular language? Because what is there, if you know what is regular language, if you know, you can clearly understand later what is non-regular. Okay, we are only trying to learn right now what is regular, how better we can understand with various representations like regular expression, finite automata, and in future regular grammar and so on. Let's begin with finite automata. You know, the regular expression is the simplest representation for representing a regular language. Now we have another model to represent a regular language, which is finite automata. Here you should have the models like deterministic and non-deterministic machines who are going to represent a regular language. To begin with, first you should know what is the automata, right? First time we are dealing with finite automata. So what is this automata, which is a Greek letter to represent the machines? Like automata is a Greek word which to represent machines. Automaton is a singular word to represent one machine, but automata can represent a singular or plural, where this automata is a machine to represent a language. The finite automata is also a machine to represent a regular language. If you have a finite automata, that means you have a regular language. But how it represents a regular language? It's going to follow a definition and configuration which helps you to understand the various parameters. Like whenever I say finite automata, you will have set of parameters q, sigma, delta, q naught, f. These parameters will help you to understand the model. This model will represent a regular language. How it represents? The q is basically what? Set of states. So you will have the states. You want to know a particular machine, you can see I'm just drawing a machine here. Don't worry, what is it? You don't need to worry about it. Okay, some machine. Here every circle represents a state. How many states are there? 2 states. So somebody can say Q is nothing but 2 states. Set of states, right? This set will have 2 states. So set of states. How many states? Must be finite. You can't have infinite number of states in the diagram, right? In the graph or in the diagram, you can't have infinite number of circles. You should have the finite number of circles to understand the problem. Right, sigma. This is set of symbols. It's nothing but alphabet. Then who are the symbols? Here, small a and small b. That sigma is alphabet. It's nothing but a comma b. And what is delta? That's what you require to understand. This delta takes time to know the definition of a DFA, NFA, and this is going to help us to know about the different types of machines in finite automata. So it's just now I can call it as transition function. But what is the transition function? What is the transition function? Here delta for DFA, delta is q sigma, which is a Cartesian product of q sigma, will map to q, whereas NFA delta is q cross sigma that maps to 2 power q. This is without epsilon. There is another NFA with epsilon, that will be, I'll just write NFA again, but with epsilon moves. Q cross sigma along with epsilon, it maps to 2 power q. There's no much difference between NFA without epsilon, with epsilon moves. And the various types of machines in finite automata, each one mapping will be different. Like the first one is deterministic mapping, the two are non-deterministic. So we'll see them slowly. Okay. Q naught is every machine has the initial state. Every DFA has initial state. Every NFA has initial state. Okay. So Q naught is initial state or starting state. And remember that this Q naught is here A. Q naught is what? A. And this must belongs to one of the state in the Q only. If you ask me what is Q naught belongs to Q only. Is one of the state in the Q is acts as initial state. And what is F? Don't say just final state. It could be 0 or more final state. Sometimes no final state might present in the machine, right? So set of final states could be 0 or more. That is the meaning. Set of final states. Here, how many final states are there? Only one. So you may say that F is here. What is it? B. That's why you will represent in the set, because sometimes no final state, you must represent empty set here. If you have more than one, let's say A and B both are final, then you have to write A comma B here. So it depends on how many finals are there in the machine, and that many states you must write in the set. Fine. This is how you write or you represent the finite automata. And how this machine reads basically, right? I have just drawn the diagram, but maybe you don't understand now, as I have not explained clearly how to read the strings in the machine. To understand this, first how this is configured with these 5 parameters. Okay, how this is configured. Let me explain with some diagram configuration. Now your input will be here somehow, like I'm just reading, let's say AAB is a string, and this is called as input tape. As you are reading input symbols, you may call it as input tape. Now you will be having some pointer or head to read the symbol every time, and your control is here. This is, you may call it as finite control, where you have whole algorithm or program here. Now what is the job of finite? This whole thing represents a finite automata, where you just call it as read pointer or read head. Okay. Now you may have, machine here, let's say A. Let me see the diagram what you have. B, A. Some diagram you have here. So what happens in this? Initial state is A. And what is the current input symbol that you have under the head? A. So in this machine, you are going to run each input symbol at a time. A on A, you will move to B. The current state is here B. Current state is what? B now. Now A is already read, so the head pointer, it will move here. Then next symbol is also A. Now current state is B. From B, by reading A, it will be in the same state B, and after that this head will move here. And from B again you will read B, and you will be at B, and its head is completed reading it, right? Now what happens? The machine halts, has nothing to read next, so it halts at this state, whatever it is, doesn't matter, it halts. Now this state is B. Is this B final or non-final? That depends on what circle you have, single circle or double circle. If you have double circles, then you will say final state. As mentioned in the previous one, F is having only B because B is the final state. So double circles represents the final state. And if you halt at double circle, one of the double circle in the machine, then that string is valid. So this AAB is valid string. That is the reason from initial state, let's say A is the initial state, right? Q0. Q0, after reading the string, after reading the W, if you halt at final, that means W belongs to L. Suppose by reading the string, if you don't halt at final, that means halting at non-final, halts at non-final, then the string is invalid. So there are two types of strings in the world. One might present in the language, one might not present in the language. If it is present in your language, it must halt at final. If it is not present in the language, it should halt at non-final. So this is the behavior of finite automata. So finite automata either accepts the string or reject the string. If it accepts, it should halt at final. If it is not accepting, it should halt at non-final. So when you design a machine like deterministic machines, you must think about these two possibilities. Are you halting at a final state for your valid strings? Then you should design such a way that for every valid string, you should halt at final. If the string is invalid, you should try to ensure that you will halt at non-final, right? So this is how you check about deterministic finite automata. Now, fine, we have deterministic and non-deterministic types. Let's move on to understand the behavior of these machines. Deterministic finite automata. First, we'll focus on DFA rather than NFA or other things. We have two types of machines, DFA and NFA in the finite automata. What is deterministic finite automata? When you have DFA, so look at here, this is the main important transition function which will help you to understand what is DFA. DFA says that whenever you design a machine, look at that previous example that I have taken, right? Okay, don't worry if I draw a different machine, that's okay. I have some machine here, right? How do I know it's deterministic or not? If it is deterministic machine, from every state, like this is every state in the queue, every symbol in the sigma, you must have a transition in the queue, mapping. So here you can see q cross sigma means from A comma A, that's one combination, and A comma B, B comma A, B comma B. This is your domain, the q cross sigma. And from here, you should map to q. What is q here? A and B. Now you think about what are the mappings you have. From q, every state in the q and every symbol in the sigma, you should have exactly one mapping, one transition here. As per this definition, exactly one mapping. As per this diagram, exactly one transition. Now see, A comma A, it goes to B. So it goes to B. A comma B, it goes to A. See that? You have exactly one mapping. Also exactly one transition somehow. B comma A, exactly one transition. And B comma B. Oh, here I might return the one edge, but it's two transitions. Remember, it's not one transition. A you have one, B you have one. Two transitions we have represented in short form with one edge. So here, if anybody asks how many transitions here, not one, it's two. One for A, one for B. Okay. And B comma B, it goes to B only. Now look at, is the definition very clear? From every state, for every input symbol, there is exactly one mapping that goes to one of the state in the queue, right? Exactly one. From this, you have exactly one transition, right? And the two exactly one mapping. In the diagram, one transition, in the function, one mapping. Remember, somehow they are correlated here. Now, what is the definition of this DFA? Very simple. If you want to find the definition, just remember this: from each state in the DFA, for every transition or for every symbol, there exists exactly one transition. There is exactly one transition. Goes to the next state. This is complete definition of DFA as per the delta representation. Once you remember this, everything will be easy. Suppose you have two states. How many transitions? For this state, you have two transitions. For this state, you have two transitions. Total 4 transitions you will see. That's why you got 4 here. The number of transitions always same as q cross sigma. If anybody asks how many transitions in DFA, number of transitions that you see is definitely equal to size of q cross sigma, which is same as delta, right? That's size of the function is same as the size of the domain if you are aware of it. Okay, number of transitions always matches with this. Now let's come to this. You have now DFA definition, some of the important points. How many initial states must be there in DFA? Only one. How many final states must be there in DFA? Don't know, 0 or more. So few points you can remember in the beginning itself. One initial state, you draw any DFA. How many final states? Don't know, 0 or more. Never say that at least one is wrong. Okay, at least one is wrong. Either 0 or more final states will be there in the machine. Okay, and always remember, if there are 2 states, from each state you should have a transition for every symbol. See, from this state, A is you have exactly one, B also you have exactly one. From here, A exactly one, B exactly one. You can't miss. If I miss this one, that's not a DFA anymore. That's not a DFA anymore. Okay, let's start with the problems. If you already practiced, then it will be very easy for you to understand. How many states in DFA that accepts empty language over binary alphabet? So binary, I am taking here sigma is equal, let's say 0, 1. I want to represent what? Empty language. What is empty language? L is equal to empty set. That means I don't have a string to accept. Then you should have a special state in the machine. By beginning only, this arrow represents what? Initial state that goes right. When you begin the machine, you should go to dead state. Dead state means you don't accept any string from there onwards. So once you go here, you read anything, you stay here, 0 or 1, you always stay here, because I don't want to accept anything. So initial state itself is dead state. I don't have a final in the machine. Of course, here in the diagram you may design more than one dead state if you want. But if you want to design minimum number of states in DFA, when somebody asking number of states, that means you must take only minimum DFA. So this is the minimum DFA. How do you know that? Because I have only one state. Less than one state, impossible to design. Now how do I know this is empty language? Because I don't have a final state here. Do you have any final? When you don't have a final, you can't accept even one string. Is that clear? I don't have a final means I accept nothing. If I want to accept something, I should have at least one final. Right? So very simple. When DFA has no final, means definitely accepting empty language. But it's not necessary to design with one state. Because of minimum DFA, I design with one state. You may design with two states. See here, 0, 1, 0, 1. They're also accepting nothing, but it is also DFA, but it's not minimum DFA. Even though it is DFA, but when somebody is asking number of states, you can't consider it. You have to consider minimum DFA. Clear this point? Okay. For any regular language, how many DFAs are there? Very important question. You tell me now. I just shown 2. Can you draw one more? Just try. Don't ask me, sir, why are you designing this way only? Your choice. How do you design? Another DFA. Likewise, with 3 states I can design, 4 states I can design, but don't keep any final. But you must satisfy DFA. You can't miss any symbol transition from every state. From every state, you have 2 transitions exactly, as you have 2 input symbols in your sigma. Clear? So the first point is, for any regular language or every regular language, you will have infinite equivalent DFAs, but only one minimum DFA. I'm just keeping a note for you. You can write yourself, for every regular language or every regular set will have infinite equivalent DFA is possible. But remember, only one minimum DFA exists. You can't have more than one minimum DFA, unique minimum DFA. Only one means unique. You can't have more than one. Fine. So these are important points for every regular language. Okay. Now what is the right answer? How many states you answer? 2, 1, 3, 4, 5. So which one is the right answer? One state would be sufficient to accept the empty language over any alphabet. You may ask question, sir, that sigma is binary. If it is ternary, what do you say? If it is unary, what do you say? So let me explain you. Sigma is equal, let's say, A. How the DFA looks like? I want minimum DFA only. A comma B. How it looks like? A comma B comma C. How it looks like? And so on. You can design as many you want it. I want to represent what? Empty language, right? For all of them, what? Empty language you want. Here, empty language, how it looks like. Initial state is not final, because if it is the final, it will accept epsilon. But it is non-final, as you don't have any string. Just keep A here. Here what do you do? Empty language. Keep A comma B. Here what do you do? Number of transitions may vary, but number of states will not vary for the same language over different sigma. Is it clear? The number of states are 1, but number of transitions would vary, depends on how many symbols you have in the sigma. Okay, number of states in all the cases you have 1. Clear? Minimum DFA will have only 1 state. Okay, and is there any final state? No. How many non-finals? Only 1. Okay, so everything that I ask, you should know how to answer it. Fine. Let me go to another question now. Can you answer it now? How many states in DFA that accepts universal language? Very famous, right? Over binary alphabet. Binary alphabet is what? Sigma 0, 1 or A, B. You can take any choice. Now, what is universal language? You know that in the regular expression you have written A plus B whole star. So that A plus B whole star is going to represent universal language somehow. Every string is present in the L generated by the A plus B whole star. Now, everything is accepted. There is nothing to be rejected. That means your DFA, just keep finals only. Don't keep non-finals. Like, if I have initial state, first point, initial state I am keeping final. What do you mean by that? When the initial state is the final, it always accepts epsilon, because when you begin, you are reading epsilon by default when I don't read anything else, right? If the string is epsilon, you will always halt at final. You will always halt at initial. If the initial is final, then epsilon is accepted. So if the initial is non-final, epsilon is not accepted. In deterministic motions, very simple. If initial is non-final, that means epsilon may not be, epsilon is not in your language. When the epsilon is in language, you must keep initial as final. Try to understand this difference. Now, after that, is there anything to reject? No, right? Everything I want to accept, any sequence over the A's and B's. So A may come or B may come, any order, right? After B, A may come, after A, B may come, doesn't matter. So this one you can also write or draw A comma B. And remember, when you're writing A comma B, doesn't mean that after A, B comes. Maybe B will come first, or again B may come, or 3 A's may come one after other, doesn't matter. This 2 means 2 independent transitions. 2 independent transitions, they can appear in any order. So any sequence over A's and B's. When we write this, it means any sequence. It could be A comma B, B comma A, or you may have 3 A's are consecutively coming, or doesn't matter. What do you think? So any A's and B's, that is the meaning. Now anyhow, both are same. How many states you require? 1 or more, just 1. Very important point. If every state is the final in the DFA, if every state is final in the DFA, what is the language accepted by that motion? Okay, DFA I'm talking about. If every state is the final, that is wherever you halt, you are halting at final. If I'm halting at final, the string is valid, means every string is valid. When every string is valid, it has to be universal language. Is that my point clear? Okay, I'm repeating again. If every state in the DFA is final, if every state in the DFA is final, if every state in the DFA is final, it means for every string you will halt at final. It means your language is universal because you are not rejecting any string. Okay, so how many states? 1. Okay, if every state is non-final, empty language accepted. If every state is final, sigma star is accepted. You may call it as this L is equal to A plus B whole star. You can also call it as sigma star, because sigma is 0 comma 1 or A comma B. That doesn't matter, you know. Sometimes you may draw with A comma B, or you may draw with X comma Y. All are same as if they are binary symbols, right? 2 symbols are there in the language. We mostly use A comma B, but as per the question, binary alphabet, nothing mentioned. You can take 0 comma 1, A comma B, X comma Y, all are same. Okay, don't worry much about it. The options, you don't worry about A, B 0, 1, X, Y. So it doesn't matter. Just number of states only matters. You just take as per your practice. If you are practicing always with 0 comma 1, just take 0 comma 1. But if you practice A comma B, because always important what your mind thinks, how quickly it thinks. If you practice A comma B all the time, you can very well design with A comma B's. Because always I practice with A comma B, sometimes 0 comma 1. I usually do very less with X comma Y. But that's fine. Let's go to the next question. Okay. How many states in DFA that accepts L where every string is having even length? I hope you know the regular expression, right? Can you write that now? Let's see who will write. Okay, just think about it. Stop the video and pause the video. Now just think about what is the regular expression to represent even length strings. Did you remember that? A plus B whole square whole star. That will represent every even length string over A comma B, right? Now, how many states required to accept this language or to accept the language generated by this expression? Think about it. Okay, what is the language? Epsilon, then one length not possible, two length. Fine. Now look at your language. In DFA, mostly, always consider most of the problems focus on minimum string. What is epsilon here? Minimum string. That will give you the beginning. Once you know the beginning, you can slowly expand the machine. So when you have epsilon, then how do you design a machine? This is how you design. Now I have accepted epsilon. How do I expand this state to accept the remaining strings? Now you focus. The problem is even length, right? Means every second symbol, whatever it is, you should come back to final. That means just take the auxiliary state, one length, either A or B, doesn't matter. Two different transitions, either A or B, you go to non-final because it should not be accepted. After one length, you get one more length, you come back to final. Now see, is it DFA? How do you know it is DFA? How do you know it is DFA? From Q0, one transition for A, one transition for B. From Q1, one transition for A, one transition for B. If you want to see exactly how transitions are there, you can see here, you may draw like this, but sometimes it would be appropriate in the beginning, you draw a different way. It's actually A is here and one more transition B. Instead of drawing two different edges, you can represent with one edge. Anyhow, two transitions are there, but short form to understand two transitions with one edge. Okay. Similarly, A, B. That's okay. That can be, represent short form with one edge. So how many states we have? 2, 1, 3. You can see simply two. So how many states? How many states are there? 2 states. How many transitions? If I ask here, how many transitions? 1, 2, 3, 4. 4 transitions. But question is about how many states? 2 states. Okay. So now if I ask, how many states in DFA that accepts odd length strings? Even length strings too, right? Odd length, how do you design? Think about here. This Q naught actually represent what? Even. Whenever even length comes, that you always stay here. If there is no more symbol, you will stop here. If it is odd length, you will stop here. Now you can easily understand. If even length strings you want, you made even state is the final. If odd length strings I want, I'll make Q1 as the final. If anybody makes both are final, every string will accept. But anyhow, we have a better mission for that. Okay, let's focus on odd length strings. How do you design? Very simple. We have 2 states. This is the even state. This is the odd state. Every odd length you will go there, A or B. Every even length you come back. Now you decide which one you want to make final. If I make this state is a final, I will accept all even length strings. If I'll make this state is a final, I'll accept all odd length strings. As per the question, you want all odd length strings. W belongs to A plus B whole star and the length of W is odd. It means every odd length string should be there in the language. You should not miss even one odd length string. So how many states again? 2 states. That means whether you find even length strings or odd length strings, the machine will have 2 states. Only the final state will vary. I have one more relation between these two. Okay. So first time I'm introducing that, the complement of a language. Do you believe that this question and previous question are complement to each other? Okay. So let me explain the relation. Suppose L1 is set of all even length strings over the same sigma, right? Even length strings over the same sigma. What is that? A comma B. Now this problem is odd length strings, that is, let's say L2. Set of all odd length strings over same sigma. Now what is the relation between L1 and L2? They are complement to each other. If I do the L1 complement, I'll get L2. If I do the L2 complement, I'll get L1. Then what is the beauty of this concept is, if you know DFA for one language, that means you already know the DFA for another language. How is that possible? So look at the previous one, L1. When you want even length strings, this was the final and this was the non-final. Just if you interchange all the finals, you make non-final, all the non-finals you make a final, you will get the complement of the language accepted by the new machine. Okay, so it's a very important. It is applicable only for deterministic finite automata. This concept please don't apply for non-deterministic machines. Okay, will not work. So in deterministic machines, the complement of the languages would be so easy if you know the DFA for any one of the language. Okay, these two languages are complement to each other. If you know DFA for any of these languages, you will get easily for the for other language DFA construction. So now you can just apply what is the definition of the complement of a regular language to design a DFA. If you know DFA for L1, I'm just saying for L1, if you know the DFA, what you do is just interchange finals and non-finals. So F, NF means NF means non-final, F means final. All the finals you make non-final. Here only 2 states are there, but you may have 5 states sometimes. Whoever the final, make non-final. Whoever there is a non-final, make final in this DFA. So what do you get? You get some modified DFA. Modified DFA. This DFA will accept L complement. Okay, I've seen some people saying that complement of a machine. We don't do the complement for a machine. Remember that. There's no meaning for that. We do the complement for the languages. For that, there is an algorithm to design a DFA. We take a DFA, interchange final non-final, we'll get another DFA. That DFA accepts L complement. Okay. Similarly, if you have a machine for L complement, same approach. Design a DFA, interchange final non-final, you'll get some modified DFA that will accept L1. So conversely also it holds. Fine. That means, can I say that L is a regular language? Then L complement has to be regular language. So many relations are there, okay, in this topic. Fine. Oh, you have 2 states, right? Let's move. How many states in DFA that accepts L, where now the number of A's is even, not the length of the string, both are different, right? Number of A's is even. Can you write expression for this? Number of A's is even. Did you remember that? You know, so many expressions I have written, right? Number of A's is even, like A, this can be repeated any number of times, right? Whole star, but B's can come any point of time here. But obviously, this would take much time to understand, no doubt, right? So that B star you can write as a plus B star, or B star you can append here one more if you want it. So many equivalent expressions for this problem. Anyhow, but DFA is so easy rather than expression. Sometimes regular expression might be easy for you, as you know, you don't take much time to write, but sometimes DFAs could be easy to design. Sometimes even NFA, sometimes grammars. You know, it all depends on how you practice, how you understand the approach. Now come to the point. This problem, I feel DFA is so easy. Why? See here, number of A's is even. Now your focus is on number of A's only, right? This is for even A's only now. B's doesn't matter for me. Sorry, odd A's. Now when one A comes from here, I'll go to odd A. One more A comes, I'll come here. See here, the problem almost solved but not complete. Why? Because B's also may come in our problem. B's may also come in our string. Then what do? From this any number of B's we don't count. From this any number of B's we don't count. See that the problem is solved or not. I did not take much time to think about it, right? I should know how to, understand the even number of A's. Like I understood even length strings, now I'm understanding even A's. If it is even length, I will write A comma B here. If it is even A's, only A's I will take a transition, because I have to remember A is not the B's. B's can come any number of B's anytime, right? That's why B's we keep self loop, and we don't have any condition over the B's. That's why we have self loop everywhere. Okay, now is it satisfying? Is it accepting all the strings who are having even number of A's? Let's see that. When there is no A, it might be epsilon, it might be only B's. When there is A, odd A, if one more A comes, then only it comes final. Otherwise, it will always here. Okay, so this will definitely accept all the strings who are having even number of A's. How many states you need? Just 2 states again. Okay, would be easy, compared to this expression. This motion would so easy for you, because you have understood even length strings, even number of A's, and obviously similar, except this self loop concept, because B's have no condition. That's why we have a self loop. We are not looking for the B's at all. Okay, how many states in DFA that accepts the all strings where each string is having at most 3 length? At most 3 length. Okay, I did not write an expression, but let's try. What is at most 3 is? Did you remember this one? Sorry, at most 3 is, sorry, the at most 3 length, right? Not 3 is. At most 3 length. At most 3 length. Now let me explain you. What is at most 1 length? How do you write at most 1 length? A plus B plus epsilon. This is going to represent at most 1 length. Why at most 1? 0 or 1. 0 means epsilon, 1 means either A or B. Now you want at most 3 length. How do you do that? This one only you take 3 times in a sequence. That is A plus B plus epsilon 3 times, that means power 3, which will represent at most 3 length. When you write 3 times in concatenation, you will get A plus B plus epsilon whole power 3, which will be at most 3 length. In case if you try to generate 4 length, impossible. Why? A in power 1 and in other power 1 you can take A or B or epsilon, whatever it is. At most you can generate 3 length. Minimum 0. How? Everywhere you take epsilon, you get epsilon. Okay. So this is what you can write as an expression. Now, what is your problem? Your problem is how many states in DFA? Okay, concept is very simple. You have to track till 3 length. After that, anyhow, you don't have acceptance. So first 0 length, is it accepted? Yes. This will represent 0 length. And 1 length. So you have to move it to remember that 1 length, right? Either A or B. You must go to the another final, but this one will guarantee 1 length. So if you have 0 length string, halt here. If you have 1 length string, you halt here. 2 length string, you halt at 3rd state. And 3 length, you want to accept? Yes. So 3 length, you go here and accept that too. But after that, you can't accept it. So we have a special state called as dead state or reject state. Now, any string or any length that is beyond 3, you go to dead state and stay there itself. So this is length of W greater than or equal to 4 or greater than 3. Now, you give any string in the world, I'll definitely have a path. How many paths you will have? Exactly 1 path. That's why you call deterministic motion. Fine. So at most 3 length. So till 3 length, 0, 1, 2, 3, you will accept. After 3 length, you will reject. How many states you need? 1, 2, 3, 4, 5 states. And always you cross check after designing, did you make deterministic transitions? From here, A exactly 1, B exactly 1, A exactly 1, B exactly. From every state, every symbol, exactly 1 transition should exist. Not 0, not more than 1. It should be equal to 1, exactly 1 transition for every input symbol. So you will have 5 states. 5 is the right answer, right? And this dead state should be involved or counted in DFA. You can't ignore any state, whether it's dead state or not, doesn't matter. If the dead state exists, you must count in the number of states. As it is deterministic motion, it always count if dead state exists. If not exists, you should not count. So please try the next one. How many states in DFA that accepts L, where L is having all the strings who are having at least 3 length, which is so easy, right? At least 3 length. How do you do that? At most 3 I have explained. Now at least 3, how do you do that? A plus B, 3 length you should guarantee, minimum 3, but after 3 length, any length should be okay. So guarantee 3 length is there. Because there are many other expressions to represent this language, just very simple one. This will guarantee at least 3. This will be 3. This will be greater than or equal 0. Will definitely guarantee greater than or equal 3. Fine. And now how to design DFA? Already have designed, not takes much time. Now at least 3. So first go for the 3 length. A or B. 1 length. See here. Now 0 length I am not accepting. 1 length also I am not accepting. 2 length should not be accepted. 3 length should be accepted because minimum 3 length should be. But after that, every length or every sequence should be accepted. So this state is going to be greater than or equal to 3. Should not go to the new state. Why? Because if you go for another state, you are increasing the number of states. But we always design minimum number of states in DFA. That's why this DFA is minimum. In case anybody going for new state, that is also correct DFA, but not minimum DFA. Remember, in case you want to find the number of states, you should think minimum DFA, not just DFA. Right? Designing DFA is one challenge. The second challenging is I will design minimum DFA, because your DFA is also accepting the same language, but that may not be minimum DFA sometimes. Okay, how many? 4 states, where here dead state is not needed. Dead state is not needed. So here 4. Okay, now yeah, very interesting question, where in the exam you don't need to design anything. Length of the string is divisible by 3, then there are 3 remainders, so 3 states. That's it. But anyhow, we should know how to design it, right? Length of the string is divisible by 3. How do you design it? You know, when the string length is divisible by 3, what are its remainders? Lengths, 0, 1, 2. These are only 3 remainders, right? When you divide any length with 3, 0, 1, 2, 0, 1, 2, that's all. You take 100 length divided by 3, you definitely get the remainder 1, right? So somehow the remainders are 3 remainders possible, 0, 1, 2. So there are 3 states maintained to understand that the length is divisible by 3. So one remainder is for 0, let me say R0, which is initially epsilon, our initial state, R1 and R2, that's all. Now these 3 states would be sufficient to understand the length of the string is divisible by 3. Now see, this transition will cover the 1 length. So remainder 1 comes when you divide with 3. The remainder 2 length, or remainder 2 when you divide with 3. Now when multiple of 3 comes, you will get remainder 0 always, because you are dividing with 3. And your problem is divisible by 3. Any string length which is divisible by 3 must halt at final. Now tell me, which state represents the string length is divisible by 3. So whenever the string comes here, that string length is divisible by 3, because the remainder is 0. 1, 2, 3, 4, 5, 6. Every time is a multiple of 3. Then you will halt here. Okay. So this R0 will be final. What is it? R0 will be final. Here every state has a meaning. In case if you make R0 is a final, that is divisible by 3. In case if I make R1, R2 both are final, then that is not divisible by 3. So complement of this. No doubt. If I say length of the string is not divisible by 3, then you will make this 2 are final. You may ask, sir, if I make only R1 is the final, what is the language? Yes. So everyone has a different case. Like, let's decide who is going to be the final for what situation. Suppose you want to know length of the W is divisible by 3. That's length of W mod 3 is equal to 0. That's the situation, right? Divisible by 3 means remainder 0. Then in that case, who is the final? Who is the final here? Who is the final? R0. Okay. So I'm just designing only final states because the motion is same. If suppose length of the W mod 3 not equal to 0, who is the final? R1 and R2. R1 and R2. In case length of mod, the length of the string mod 3 equal to 1, means remainder 1. In out of this 3, who is going to represent remainder 1? R1. So we'll make R1 as a final. Length of the string divided with 3, you got remainder 2, then you will make R2 as a final. It's so simple to design a DFA which is going to accept different strings based on the modulus condition. If the remainder 0, make the 0 is final, remainder 1, make 1 is the final, remainder 2, 2 is the final. If remainder is not equal to 0, means not divisible by 3, means 1, 2 are final. So simple to design such DFAs. But over all of them, the number of states will be 3. Number of states is 3. Easy? Okay, let's move on. How many states in DFA that accepts L? Oh, it's so easy now. I have already explained how many. Doesn't matter, right? Now I don't need to design, just say 3 is the answer. Okay, I've explained just now. R1 will become final if you want to do this. Okay, this is a different question. It's not about the length of the string, it's about number of A's. So slightly change the problem is number of A's in a string is equal to 3. Now, what would be the regular expression for this? What would be the regular expression for this? How many A's exactly? 3. So 1A, 2A, 3A. 3 A's exactly. But how many B's? Don't know. Any number of B's can come. So you just write B star could come, any number of B's can come before first A, or in between the first 2 A's, or in between the last 2 A's, or at the last. So this is an expression to accept or to generate the language where the language is number of A's is exactly 3, but over A's and B's. Now how to design? Very simple. You know the concept, right? Exactly 3 A's. Who is the minimum string? You just remember minimum string. Answer will be so simple. 3 consecutive A's. So for this, first you design the machine. 3 A's. 1A, second A, and that's all. You don't have any more. If you get any more, you go to dead state. Now from here, if B comes, should I accept? Yes, B's can come any. I don't have any condition over the B's, right? Only A's should be 3, but B's have no restriction. Any number of B's after A, any number of B's. See that formation also same. B star A, B star A, and again B star. Any number of B's after A, any number of B's fine. But after this third A, if you get one more A, you should not accept. So what do you do from here? If you get any more A here, because fourth A might come, might be possible, you should never stay in this path. Right? You should go to dead state and stay there, and any sequence after that should reject. Fourth A should never come. In case if it comes, go to dead state. How many states are there now? 5 states. The answer will be here. This is how you design a DFA to accept exactly 3 A's. Okay. Now, more than 3 A's. More than 3 A's means at least 4 A's, right? More than 3 means at least 4. Now, the question is number of A's of W greater than or equal to 4. That is the meaning greater than 3 means. Now, greater than or equal to 4. How many A's you should guarantee first? 4 A's. 1, 2, 3, 4. Then after this, do you have any condition? No. I have satisfied minimum 4 A's. Now I can have 5 A's, 6 A's, 7 A's because minimum 4 A's. But number of A's could be beyond for any count. So now here it can be A's or B's, no restriction. If you want to write an expression only I'm talking about. You can have any sequence of A's and B's. Very simple expression to represent at least 4 A's. Okay, I hope you know how to write an expression now. Now I want to design the DFA. Who is the minimum string? 4 A's. That will give you an idea how to understand the problem. Four A's. 1A. You should know first 4 A's how to accept. That's the minimum condition I have satisfied. Fine. Now you need to guarantee that all the strings in the world should have a path here. Otherwise your machine is wrong. DFA means deterministic. You give me any string, I will have a path to one of the state in this diagram. Okay, that's why I should think about what is missing here, B, what is missing here, B, what is missing, B, what is missing, B, what is missing, both A and B. When you cover them, then only this machine is DFA. Never leave in the middle of the construction. Okay, let's focus on what is here, B. Now here you can see before this A, are you counting any B's here? No, right? I can keep blindly B self flow. I don't have any issue with the B's, right? Any number of B's can come. But somewhat this expression and this diagram may not match directly, but internally the same meaning. Okay, because only B's we are thinking here, not A's. A's already covered. Here A is covered, B's. Oh, already 1A is covered. B's I can stay here. Because I did not say 4 consecutive A's. I said I want at least 4 A's. That can come in any sequence, right? And after second A, any number of B's. After third A, any number of B's. After fourth A, because 4 A's guaranteed. After fourth A, A's or B's doesn't matter because minimum 4 A's satisfied. Here you will have A or B. Here why didn't you keep A self flow? Because A already I have covered. I keep on counting A's. Whenever I want to remember, I change on A, right? After this I don't want to change on A because I have satisfied my condition. Now A or B I can stay in this final. So this is a DFA. How many states now? 5 states. Okay, I'll give the next problem as challenging that you should design now. Just take time, pause the video and try to design this. I've explained greater than or equal to 3, greater than or equal to 4, and just think about it, how to design it. Okay, question is number of A's is at most 2, not at most 3. Less than 3 means first have a clarity. At most 2. At most 2 A's. You can write an expression something like this. A plus epsilon. A plus epsilon. I'm just writing an expression to have a practice. This will give you at most 2 A's. Anyhow, we don't need this expression to design a DFA. But it's another practice parallelly that you can write regular expressions along with the DFA. Okay, how many states in DFA that accepts L? Okay, done. Now focus again. 0 A is accepted, 1 A is accepted, 2 A is accepted, but third A should be rejected straight away. How you do that? No A accepted, fine. 1 A accepted, fine. B's don't worry right now. 2 A's accepted, but third A, what should be done? Rejected. And after this, we'll make a DFA properly. We'll go to DFA. Doesn't matter after that, anything comes, will stay there. But it's not yet over, right? Now, so many transitions are missing. You should try to cover them. So, can I have a B before A? Yes, any number of B's can come. So, I can wait for A. After 1A, any number of B's can come. After 2 A's, any number of B's can come. Now, is it accepting all the strings who are having at most 2 A's? So, till here, at most 2 A's. Anything you do, it's accepted because till you didn't cross the number of A's, at 2. Once you cross 2 A's, now you got the third A, everything is rejected. because you are going to dead state. What is the dead state definition? Once you reach the dead state, impossible to reach a final. There is no path from this dead state to final. So this state is called as dead state. Remember the definition of dead state? If that state has no path to the final, then it is called as the dead state. Okay, a DFA, you may have multiple dead states, but no use. In the minimum DFA, you just have one dead. Remember that? You can design more than one DFA. More than one dead state in the DFA, but no use, right? Even though it is correct DFA, but if you want to design minimum DFA, then always keep one dead state if needed. But if anybody is keeping more than one dead state, that's okay. Don't say that's wrong DFA. That's the correct DFA, but that is not a minimum DFA. Fine. Okay. How many states? 4 states. Okay. Yeah. Very nice question, I feel. Take time and pause the video again, and please try to design and find the number of states very quickly. It would take maximum 1 or 2 minutes, not beyond that. Okay, number of A's is exactly 3, but starts with a B. That's a very interesting question, right? You must start with B. You can't start with A. So B always there in the beginning, first position, that too. But after that, you will have exactly 3 A's, and B's have no restriction. B's have no restriction. So somewhere you have 3 A's, exactly 3 A's. How many B's? So any number of B's might be here. We don't care. Any number of B's here, any number of B's here, any number of B's here. But condition is very clear. The string should start with B and it should contain exactly 3 A's. And fourth A never happens. You will never start with A. And any number of B's would be fine. How many things are there? So what is the minimum string? If you look at this expression, the minimum string is B followed by 3 consecutive A's, because other B's are optional, right? This is only the string which is having the minimum number of symbols, 4 symbols. Okay, let's design the DFA with the help of the minimum string. B is must, and then 3 A's overall. By looking at the minimum string, you always design this motion. Now try to cover the missing transitions. Here, can I have A? Can I start with A? Impossible, right? So what do? You go to dead state. Go to dead state. Yes or no? Why do you go to dead state? Because string never starts with A. It's clearly given that starts with B. Now, from here, any number of B's can come because I'm looking for the 3 A's after I start with B. In the process, if I get any number of B's, I'll wait for the A's. After 1 A, if I get any B, I'll wait for the 2 more A's. After 2 A's, if I get any more B's, I'll wait for the 3rd A. Once I get the 3 A's, I don't care for the B's. I can have any number of B's, but I should never have the 4th A. So after 3 A's, if I get a 4th A, then I'll come to dead state. I hope it's very clear. If you know the pattern, if you know the sequence, it will be very easy to design. Okay, so it almost looks like what I have written here: B, B star, A, B star, A, B star, A, B star. Those paths which are going to dead state, we don't care. Okay, how many states? 3, 4, 5, 6. You have the 6, no, right? So we'll go for none of this. So 6 states you have here. Okay, it's more interesting than the previous one, which looks similar to the previous, but have a trick or have a some interesting parameter that you need to observe. Let's see who can do that. So when you watch this video, please pause for few seconds and practice this, as rather than watching, you always practice while watching it. Okay, starts with A but having exactly 3 A's. What is the meaning? The string should start with A but having exactly 3 A's. So starts with A but exactly 3 A's. Somewhere this other 2 A's. But start, this has to be start. But overall, this is also counted in the 3 A's. Don't assume there are 4 A's, wrong. The total number of A's should be 3, but string should start with A. Okay, the W should start with A. Now, can I have the B star here? No, because I can't start with B. Can I have A star? Impossible, because maximum 3 A's. And you can have B star here. You can have a B star here. You can have a B star because we don't count the B's at all. That's all. You have an expression. Now, by looking at this, what is the minimum string you have? A. Once you have the minimum string, things will go very easily. 3 A's, but need not be consecutive. Only the minimum string will have the consecutive. Okay, now you should start with A. In case if the string starting with B, what do? You go to dead state. You can't start with the B. Okay, that's missing transition from the initial state. What is missing here? B. As I told, after starting with A, doesn't matter how many B's comes. Just keep a self loop. After having 2 A's, any number of B's fine. After having 3 A's, any number of B's would be fine. But if A comes after the 3 A's, then it should not be in your language, right? The string is crossing the 3 A's. So the 4th A should go to dead state. It will be invalid string. Okay, how many states again? I think this time is the 5 states. Okay, including dead state, total 5 states are there. In case if I miss any transition, any motion, so please take care of this. But more fully, 99% I will not miss any transition as I am looking at every state. See, in all the machines, I design in such a way that I don't design randomly. I take the minimum string. I always start from here and go next, so that my whole machine is perfect. In that process, if I miss any transition, please take care of that. Okay. How many states in DFA that accepts L where number of EAs is equals to 0 mod 3? What is the meaning of this? Don't confuse much. It is nothing but number of A's of W is divisible by 3. Very simple, right? 0 modulo 3 means what? Divisible by 3. You already know, right? Length is divisible by 3, 3 states. Number of A's is divisible by 3, will also be 3 states. But where is the difference? Think about it. Where is the difference? Length of the string is divisible by 3 states. Number of A's is also divisible by 3. Number of A's in a string is divisible by 3 is also 3 states. But where is the difference? In the exam, you can answer within 2 seconds. Right? Difference is when you say the length. A or B, you change the state. But here only A's you change the state. For B's, you put a self loop. That's where the difference is between length of the string and number of A's. Number of A's means focus is on A's. So remember the A's, not the B's. Length means either A or B. It's length only, right? So you will change the state. Anyhow, let's look at. Now how many remainders you will have? 3 remainders. 0, 1, 2. No A. If you get 1 A, go to the remainder 1. When you get the second A, go to the remainder 2. When you get the third A, come to the remainder 0. And this state is the final. And where is the difference between the length? In the length, A or B you change the state. A comma B, A comma B, A comma B. But here, B's we don't care. Only A's we are counting. So every A you are changing the state. B's what you should do? You don't count, because that is not going to count the number of A's. You put a self loop. Number of states, 3 here and there, but there B self loop you don't have, as you are counting A's and B's. A or B will consider as one length. But here A is only counted to check this condition where A is divisible by 3 or not. Now A is divisible by 3. Okay, let me write. This state is A0, A1, because as I am counting the remainder. Okay. Now if I make the state A0 as a final, you got the number of A's is divisible by 3. If I make A0 as a non-final but A1, A2 both are final, then number of A's is not divisible by 3. It's a complement. If I make these two are final, this is non-final, then obviously it's a complement of this language, right? In case only if I make this is the final, A1 is the final, then number of A's is equal to 1 modulo 3. If I make only this is the final, 2 modulo 3. So all depends on your condition. If you know this motion, you can solve a lot of problems which are depending on this divisibility. Fine. How many states? 3. Of course, this can be answered in 2 or 3 seconds after reading this line. Okay, 5 seconds at least. Okay, I think okay, this is different. Not equals to 2 modulo 3. Equals to 2 modulo 3 what? We'll make A2 as the final. Let me design the motion first. Okay, we have A0, we have A1, it's about A's only, right? We have A2. And every A, you are changing the state to see the multiple of 3 concept. And B's, you put a self loop. Now, who will be final as per the question? Number of A's equal to 2 modulo 3 means this 2 will be final. Not equal to 2 means other than this 2, you will make this 2 are final. That's it. But again, the number of states would not vary. In the exam, designing DFA is not important. Understanding what DFA needed, right? Who is final, non-final, it may take time, few seconds, but you already know it requires 3 states. Go blindly here. Okay. So remember, unless you have some trick in the question, you don't need to wait for designing a DFA. You already know divisible by 3 concept, 3 states, doesn't matter, only the finals are different, but whole machine is same. Then make 3 as a number of states. Okay, it should take, just as per my knowledge, it will take max 5 to 10 seconds if you have solved this kind of problems during practice. Oh, number of states. Oh, this question is, see the difference? Here you have A comma B whole star, and here you have A star B star. That's all you need to observe. W belongs to what here? There is a language over A star B star. So W here belongs to the language generated by A star B star. How it is different from W belongs to language generated by A plus B whole star. Okay, this was the previous concept we are solving. W belongs to A comma B whole star. We were always taking from here, but now you need to look at A star B star. What is A star B star? What is A plus B whole star? Let's focus on that. A star B star means the strings having a particular sequence. A's followed by B's means it may be epsilon, or it may be only A's you have, like only A's, A, double A, triple A, or only B's, or you can have A, any number of B's like AB, AAB, or A double B. But the sequence is very important. Double A, double B, so on. But you will never have after BA. It's very clear. The string will have the A's followed by B's. That's all. A's may be present, or B's may be present, or no A, no B present. If both are present, A's followed by B's. So you have the few things to observe. Epsilon is valid. Of course, in this only, I'm not talking about this. Here, only A is valid, only B is valid, and both are valid. A is followed by B is when both are present. All the 4, when you combine, you will get A star B star. Look at what I have done. When nobody is there, epsilon, only A's are there, A plus, only B's are there, B plus. When both are there, A plus, B plus. So these 4 combinations are there here. In this, we are going to look at our condition that number of A's is equal to 2. and number of b's equal to 1. That means this 3 will not be there. Only in this, when a is 2, when b is equal to 1, that is straightforward, right? It's just one string, double a b, that's all. This is your language, one string only. You don't need to think much about, right? This is having infinite strings. From them, a power 2 b power 1 is your problem. How many strings? One string. Can't be designed. Double a followed by b, everything else you go to dead. We don't have any combination other than this one string. So easy to design, right? Anything you go to what? Dead state. Anything else? Here b cannot come, here b cannot come, here b is there, a cannot come, here a or b cannot come. As you know, only one string should accept a, b, no other string. So how many states required? 5 states. Click answer. Fine. Okay, similarly, I'll be giving you a lot of homework questions. You can practice and answer it, the number of states below this video. So let me show you some of the questions you should practice at any cost. In case if you have a doubt, you can post your doubt below this video in comment section. I'll be replying it. So next question is homework for you. How many states in DFA that accept cell where the same concept a star, b star, w belongs to, but a is greater than or equal to, b is equal to 1. So how do you write it? A, at least 2, right? A power, so here I'm writing here a power 2, a star. Of course, together you can write some other way too. I'm not doing that. And b, that's it. So this is your problem. And language will have a lot of strings, but minimum string will be double AB. So if you design double AB, then your problem will be simple. So this is your expression. This is your language. And now you try to accept all the strings from this expression and tell me how many number of states. I hope you can do it. Please take it as homework. And I believe you can answer it very easily. Okay, you may represent many other ways, like, a plus b or a plus ab. I don't care how do you write it. All are same. But you should know how to design the DFA for this. Take a minimum string. I'm giving hint, double AB. So how do you do that now? How do you do that? I should have 2 A's. I should have 2 A's must, right? In this process, beginning B should never come. So if B comes, go to dead state. Once you have the B, only one B. So after B, either A or B, go to dead state. Because second B never be there. And after B, A never comes. The sequence has one beauty is here, that after B, A never comes. Before A, B never comes. So these points you should remember as you have a sequence, right? So when you have a sequence like A's followed by B's, the many things you can easily observe. Fine. So I believe you may answer something here. So I'll see below this video your comment whether it's right or wrong. Okay, next one. Very interesting, and this was gate PYQ multiple times, not one time again. Number of A's is divisible by 2 and number of B's is divisible by 3. So when this question comes, the straight away the multiplication 2 multiply with 3, 6 states is an answer. Of course, you should know why the 6 states comes, but in the exam answer is 6, but before the exam know why it is 6, right? You should save your time in the exam, right? You can't design even you know it. Okay, now why 6 states? The reason is number of A's when you divide with 2, you will have 2 remainders. Let's say A0 and A1. 2 remainders for A's when you divide number of A's with 2. When you divide number of B's with 3, you will have 3 remainders for B0, 3 remainders for the B's, B0, B1, B2. So overall, you may have any combination like A's could be any remainder, B's could be any remainder. So when you look at the Cartesian product, 2 multiply with 3, you will get all the 6 combination. Like you should know, sequence doesn't matter. A0, B0, B0, A0 doesn't matter. Like A0, B0 one state. Now A0, B1 another state. A0, B2. Oh, don't assume that after a B comes. We are not talking about after a B's. You can write B2, A0 also. Doesn't matter here because W is over A comma B whole star. A1, B0 and A1, B1. Combination only I am talking about. A1, B2. So this many states are there. Initial state is A0, B0. And the meaning I have written, the meaning of every state, when you stay here, it means the number of A's is divisible by 2 and number of B's is divisible by 3. So every state has a meaning. If you stay here, if you come here, if you alt here, number of A's is not divisible by 2. It means 1 modulo 2. Number of B's 2 modulo 3 when you stay here. And when you stay here, number of A's is 1 modulo 2. Number of B's is divisible by 3 because B is 0. So whenever you see B0, B is divisible by 3. Whenever you see A0, A is divisible by 2. So 2 for A's, 3 for B's. So remember the relation. Now very simple, whenever you have A's, count on A's, always divide with 2. Whenever you get the B's, count B's, but always divide with 3. Let's do it. Now from this, A comes. Already A's are 0 here. If one more A comes, the 0 become 1. So look at here. A0, if one more A comes, it will become A1. B will be same. B will be same. So you will go there. So here look at, on 1A, just increase the number of A's. Increase the number of A's. Okay. So from every state, I'm going to do that. From this state A covered and from this state B I will cover. If I increase 0 to 1, because I'm getting a 1B, do I go here? Check. B0 become B1, but A should be same as I'm not counting A's to move from here to here because B's are only coming. Okay, from this state, A and B covered. Similarly, can you do for every state? From this state, cover A and B. If you get A, this 0 become 1. So you will get here, B should be same. A. And if you get a B, B1 become B2, but A's will be same. Okay, from this state, if A comes, 0 become 1. But always remember, when it crosses 1, then you must divide with 2 because remainder never be 2. It should, when 2 comes, remainder has to be 0. So now when A comes, 0 become 1, but B's will be same. Now look at here. When B comes, B2 become B3, but B3 will not be there because B3 means B 0. Remainder has to be 0 when 3 B's comes. So A0, when B2 become B3, A0, B0 happens here. So when third B comes, the B2 followed by B will become B0 as you are dividing with 3. So which is on B. Similarly, now here, if one more A comes, it's already 1A, right? One more A comes, it will become A2, but A2 divided with 2, that it will become A0. So we will go back here. And B, B0 become B1. I hope you understood, then copy paste. A1 become A0 by adding one more A, and B comes, we will go here because B1 become B2 and A will be same. And here, if A comes, A1 become A2, but 2 divided with 2 is 0, remainder. So we'll go there. B, you come back. B2 will become B0. Fine. So this is the machine where number of A is divisible by 2 and number of B is divisible by 3. Each state has a meaning. In the exam, they may ask different way. Like A is not divisible by 2. B is not divisible by 3. Answer is here, no doubt. Except this, you make all this are final. Then what do you have? A is not divisible by 2 as well as B is not divisible by 3. So if you make, oh sorry, which one? I'm very sorry. A is not divisible by 2 and B is not divisible by 3. So you should not have 0, this two especially. If you make these two final, in both of them there is no 0. That means both are satisfying, not divisibility. Please don't make these two or these are final. Why? Because their A is divisible by 2 is there. Okay. Clearly understand what is the question is. Here so many combinations are there. So many. Okay. According to the question, both should be satisfying divisibility. So both should have the remainder 0. So we'll make this as the final. Okay. We'll make this as the final. In case if you are making these two are final, that means both of them are satisfying not divisibility. Okay. So understand the concept to make the final states. I hope this problem will help you in number of problems which are depending on these two conditions. Okay. Answer is what? 2 into 3, 6, and there is no option here. So we'll go to none of this. Answer will be 6 states. Okay. I hope you can answer it. Number of A's is exactly 2. number of B's is exactly 1. So then what is the language? It's not A star B star. Again, you need to look at each and every condition clearly. W is having any combination over A's and B's, but A's is exactly 2, B's is exactly 1. What does this means? The language is having many possibilities, like A B, 2 A's 1 B, 2 A's 1 B. It could be ABA, or it could be BAA, or anything else that I'm missing. Just check it. So 1 B, 2 A's, any order could be there. Of course, it's final language. Now, can you try I'll give some time or pause this video and please try to solve this question here. In the string, the order is not important. After A, B may come, or after B, A may come, but counting is important. So from the beginning, initial state, your focus is on when I get 2 A's on the third A, I should go to dead state. When I get 1 B, it's fine. When I get the second B, I should go to dead state, because second B never comes. So this count you should remember, right? You need to keep track of the count, how many A's and how many B's. Let's start with the count. Any problem that I take in this pattern, you just remember how I follow in designing DFA. The counting is very important. Initially, what is the count? Count is, I may write, A0, B0. Doesn't mean that after A, B comes. It could be same as even B0, A0. Because here order doesn't matter, right? Count only important. So please note down that. Okay, I'm writing here A0, B0. It also means B0, A0. Okay, remember that point. Accepted or not? No. When it will be accepting 2 A's, 1 B. So that is your target. A to B1 is your target. What is it? A to B1 is your target. After 2 A's and B1, okay, I'm not writing power, I'm writing subscript, means order doesn't matter. Remember that way. In all of them, we have A to B1. Now, if A comes here, what is the count changing? A1, B0. Keep track of it. Okay. Whenever crosses your count, go to dead state. Whenever you reach the count, go to final state. And when you get a B from here, A0, B1. Okay. Now, from here, if A comes, that's going to be A2, B0. If A comes, or A is over, if B comes here, that's A1, B1. And 1, 2, both are covered. And third one, from here A comes, A1, B1, already there. So go there. Very simple. But here one more B comes. Already 1 B is taken. Now A0, B2. We don't have a 2 B's possibility. So we'll go to dead state. I'm just taking a dead state here. Dead state. It's crossing our limit. Our condition is failing because of 2 B's are coming, right? After this B's, doesn't matter A's or B's, we don't count. Now from this A and B covered. Now from this, one more A comes, it will be A to B1. So that is our target, right? So I can take this A to B1 as a final here somewhere. This is our required one. So one more A comes, I'll go here. But one more B comes here, the A1, B2. Oh, B2 impossible, so we go to dead state. So that counting is important. Counting is important. Now from this, third A, is it possible? Impossible. So already A2 is there. If one more A comes, we are crossing the number of A's. From here B comes, A to B0 become B1. Oh, that's a valid string. Now from A to B1, already the maximum, right? 2 A's, B1s. From this A or B, you will be crossing the limit. Now see how easy if you can keep track of counting. Now you may ask, sir, how these 3 strings are accepted? Look at the paths to reach this final. One path, second path, third path. That's all 3 paths are there to accept these 3 strings. You can check AAB. So where is that? AAB. ABA. See that? ABA. See this BAA. BAA. That's all. Any other string will go to dead state. Any other string will go to dead state or will halt at non-final somewhere. Okay. So how many states are there? 1, 2, 3, 4, 5, 6, 7. So here 7 answer not there. So we'll go to none of this. So 7 states required for this problem. So I hope similarly you may solve the questions which are depending on this. But here I have said exactly 2, exactly 1b, right? Exactly 2a, exactly 1b. In case if you have at least 1b, then after 1b, the second b should not go dead. You should put a self loop, because second b, third b, fourth b, fine, right? So when you have at least condition, put a self loop once you satisfy the minimum condition. When you have at most, then let's say at most 1b, then 0b is fine, 1b is fine, then 2b you go to dead. Okay, understand the problem and design it appropriately. Again, I'm giving this homework. I think I should solve this. Then next one you take it as homework if you have any. This number of a's is greater than or equal to, means at least 2 a's. This is at least 1b. So now here you don't have dead state. Why? At least is fine, right? It's not at most or exactly. In the at least condition, you will go till that condition and then put a self loop. Now keep on counting this one. You need to reach this one, a greater than or equal to, b greater than or equal 1. Once you reach the state, stay there. Everything is accepted. But to reach that, it will take much time. Let's do that. Initially, a0, b0. If 1a comes, that's a1, b0. If 1b comes, a0, b1. Keep doing it. And from here, one more a comes. Then a2, whenever you reach a2, put greater than or equal to, because from there, any number of a's, put self loop. So even the 2 a's, I know it is equal to 2, but I don't put, because third a, fourth a, I will stay here only. And b0 I will maintain. If b comes here, a1, b1, not there anywhere, so I have to maintain. b1, 1 means what? Greater than or equal to 1. So here also, when there is a 1b, put greater than or equal to 1, because we satisfied the minimum condition. So it's one of the important key factor. When you satisfy the minimum, put that greater than or equal to, because there you can put a self loop for the b's. Here you can put the self loop for the b's later. Now this state covered a and b, this state covered a and b, and I'm covering this state now, a and b. First, when you have a here, a1, b greater than or equal 1, you have here, right? So you can go there. See that how easy? If you don't have, you design. Now when you get a b, what do? This is what I'm talking about. You put a b self loop, as you don't need to count more. You satisfy the minimum number of b's 1. When you have a minimum 1b, that means greater than or equal to 1b. So either this b or this b stay in same state. That's why equal to 1, greater than 1, I just take one state. I don't need multiple states for that. Okay, so that is the advantage of putting greater than or equal 1. Okay, and now this state. If you get more a's, already minimum 2 a satisfied. Any number of a's, just wait there. Why you are waiting for the b? Already a satisfied the condition. Now b's you are waiting. When you get one more b, that's your string. That's when you get one more b, this is your final state, right? You satisfied already 2 a's. Now you are going to satisfy minimum 1b. So minimum 1b means greater than or equal to 1. Okay, now this one, a1 become a2, but 2 means greater than or equal to. You can go there, satisfied a. Till now, b satisfied already minimum condition, a is waiting for one more. Okay, now b, you can put a self loop, because b already satisfied. We are waiting for only a, right? B self loop. Now all these states are covered for a and b. Now this is only left. Once you satisfied both the minimum, either a or b, doesn't matter, just stay in the self loop, because more than 2 is always accepted. This minimum condition is there. So at least condition do not require dead, but when you see exactly or at most, then definitely you will need dead state. I hope you understood this problem. And how many states you have? 6. So answer will be none of this again, but here 6 states is the right answer. But previous one was a 7. There you have a dead state. Here you don't have a dead state. Okay, anything which is there similar to this, please take it as homework. And yeah, you got it. Number of a's is at most 2. Number of b's is at most 1. It's almost similar to exactly 1, right? But before this, you try to take care of all the combinations which are accepted. So many finalists might be there here. So take care of them. So it is homework. I'm very happy if you can solve and post the answer below this video. And let me know how many of you are solving this question. Okay. The question is clearly, almost which is same as the exactly to exactly 1. Only the thing is, here you will have many finals, okay. Okay, number of A's is even and number of B's is odd. Tell me, we have solved this question already. Have you remembered that already? What we have solved which is similar to this? Did you remember? Even means what? Number of A's is divisible by 2. Yes or no? And this one, number of B's is odd, means is not divisible by 2. Okay, the question is simple. Whether it is divisible by 2, A is divisible by 2, B is divisible by 3, 2 into 3, 6. Here, not divisible by 2, still answer same. 2 multiplied with 2 will become 4 states. In case if you want to answer very quickly in the exam, answer will be 4 states. But if you want to design, you should understand the property or behavior. So let's start designing the machine. Okay, so in the exam, very simple. If you know the concept or this composition trick, you can apply it. If not, you have to design the machine. Okay, so which was solved already. Like there you seen A is divisible by 2, B is divisible by 3. So 2 multiplied with 3 is 6. But here both concepts are both symbols depending on divisible by 2. So we did do 2 into 2 is 4. Okay, now how to design other way? So A's is even. So we have 2 remainders, A0, A1. B's is odd, again 2 remainders, B0, B1. Whether it is even or odd, you will have 2 remainders. That's why 2 multiplied with 2 will become 4, right? Now combinations, A0, A1, sorry, A0, B0. 2 different symbols, right? You need to track both. A0, B1, A1, B0 and A1, B1. Who is the initial state? A0, B0. So now the question is, A's is even, means you need to accept, you need to have 0 remainder. B's is odd, so B should have 1 remainder. So A0, B1, this will become final. Sorry, what I am saying. A0, B1, where is it here? This one will be final. So A's is even, then A is multiple of or divisible by 2, and B's is odd, means B is not divisible by 2. So this is the final, and very simple designing the machine. And from here, whenever even number of A's comes, you should come back. See here, when one A you go there, other A you come back. That's it. From here. And here also same. One A you go to A1, but B1 will be same. And when you get one more A, it will be remainder 0. And similarly B. B0 will become B1 if one B comes. One more B comes, that B1 will become B0. Similarly here, B0 will become B1 if one B comes. Other B comes from here, B1 will become B0. We just designed, right? When A is divisible by 2, B is divisible by 3, same concept. But so easy machine. Now look at how many different problems you can solve with the help of this machine. A0, B1 will say A's is even, B's is odd. If I make this one is the final, that is A's is odd, B's is odd. If I make this is the final, A's is odd, B's is even. If I make this is the final, A's is even, B's is even. See how many problems exist here. Okay, it's a very simple concept. If you want to answer for the gate, right, it could be answered within 5 seconds, but if you want to understand, it will take little time to design the whole machine. Fine, you got the 4 answers, 4 states. I have shown how to design with the help of remainders. Okay, yeah, decimal equivalent of W is divisible by 2. So it's a very simple. Again, the number of states will be divisible by 2, which will depend on some different property. It's not a length, it's not number of A's, it's not number of B's, it is decimal equivalent. So what is this decimal equivalent of binary? See, you have a binary concept, right? B0, B1, B2, B3. Tell me, if this binary number is divisible by 2, of course decimal equivalent of binary is divisible by 2, what do you see? What do you see speciality in this? You will never see here 1, because it's even length, means ends with 0. So you always see here no 1 here, it's always 0 here, right? Ends with 0. It's almost the same concept like ends with 0. right? This is never have a 0. It will never contain 0. Sorry, never be 1. I'm very sorry. Never be 1. It ends with 0 concept, right? If any binary number ends with 0, can I say that it's always divisible by 2? Yes, because it's even number. What is even? If binary number is having the LSB as 0, it's always multiple of 2 or even number when you convert to decimal, right? Because this all are 2 powers, you will get the even number. If you want to become odd, that B0 position has to be 1. So that never be 1 will guarantee that decimal of W is divisible by 2. Okay. There are special strings like epsilon, do you want to accept or not? Single 0, you want to accept or not? That's your choices, but you may keep epsilon or not is your trick. So ends with 0. In case if you design ends with 0, the machine, how many states required? It's 2 states, right? The same motion can be used here as 2 states. So here the answer is 2 states. Then how did you get this? How did you get this? So very simple, that all the properties, decimal equivalent of binary number will have the similar property. Like instead of divisible by 2, if you have, let's say, 4. So I'm just writing a shortcut, but if you want to design, definitely will take time. So I'm just giving the shortcut how to answer it. In case if you see that videos, please follow it. Suppose you have divisible by 4. Divisible by 4. I'm just solving it. Decimal of, shortcut I'm trying to help you, is divisible by 4. Then what is the concept you will be having? This last 2 bits should never have a 1, right? Never be 1. B0 and B1 should never be 1. Then remaining will all have the multiple of 4. So number will be definitely divisible by 4. So if you keep any 1 here, either B0 or B1, then that number will, that decimal equivalent will never be divisible by 4. That is the reason this should never be 1. So it's almost equivalent to ends with 00. Of course, not exactly same, but the same motion will be used somehow. Okay. So this will be concept similar to ends with 00. How many states required for ends with 00? Ends with 00. If you solve it, it will take just 3 states. Okay. Please try that. Ends with 00 motion, it will take 3 states. So what is the concept? Divisible by 4, 3 states. Divisible by 2, or 2 states. What is this concept, right? So remember, divisible by 2, just assume it is 2 power 1. Divisible by 4, assume it is 2 power 2. So look at this power. Look at this power. If it is 1, so if I say it's a binary number only I'm talking about, not ternary or any other right now. Decimal of W is divisible by 2 power, let's say, k. Then the straight away you can answer k plus 1 states. So very easy shortcuts for you to remember. But of course, designing the DFA will definitely take time, and I believe that you can try on your own. I have shown the trick how you do that. In case if you really want it, I can take one problem, I can do it, but work on it or remember the shortcut, that is your choice. Fine. So in case you wanted to understand more about it, please keep on watching the practice sessions that I do at the end. So definitely I'll come up with this one problem and I'll solve for you. Fine. So you have a shortcut now. Whenever you see binary number here, binary language here, and in that every decimal equivalent is divisible by some 2 power k, then just say that k plus 1 states needed. Here divisible by 4, convert this 4 into 2 power k form and k plus 1. Now I'll tell you divisible by, previous gate question, divisible by 1024. So tell me how do you do that? 1024 is nothing but 2 power 10. How many states required? 10 plus 1, 11 states. That's all. That was the gate PYQ. So decimal equivalent of binary is divisible by 1024, 11 states. Okay, don't show somebody how the 11 states, which is not required. But understand how you get this formula. That is very important. Okay. As you know, it's a crash course, so it's important to know how to answer each question in the gate, rather than knowing each and every concept at the end of the session, end of the just before the gate exam. Fine. you have the homework. Now the same question, here it is ternary. Now instead of b binary, right? T power 0 ternary number now. T power 1, T power 2, T power 3. Now divisible by 3. Same concept. Divisible by 3 means this should never be 1. This T power 0, it should not be 1. Again ends with 0 concept. So answer will be same again. 2 states will have. So here 3 powers. It is a ternary number. This is ternary. Remember that? It's ternary concept, right? So here divisible by decimal of, but don't use this formula for binary, will not work. Decimal of, this is ternary number, remember that, is divisible by 3 power k will definitely require k plus 1 states. Only the thing is language over the alphabet is different. Okay. This is another shortcut. So you may use now, this is the 3 power 1. So definitely 1 plus 1, 2 states here. Okay. You can just answer it without, designing the machine. Similarly, I can go for any language or any alphabet. It could be binary or unary, ternary, or any concept. You can solve the similar way. Okay. Ends with double B. First time I'm solving ends with double B concept, right? Ends, I have not done it. So I wanted to solve this question for you. Ending is one of the important concept in designing DFA. That's why most of the people will fear while designing DFA for ending conditions, because you never know that ending when happens. You should wait for that end. Starting means you can check, and if not, go to dead state. But will you go to the dead state while waiting for the end condition? No, that's not possible. That is the reason you should design many problems which are having ending conditions, so that you will get to know how DFA helps in understanding the problems or solving the problems which are looking a little bit difficult or different. Okay, come to the point. How many states in DFA that accepts L where the string ending with double B? So what is ending with double B? So ending with double B, before that any number of symbols over A's and B's. This is your expression. And what is the minimum string? Double B. So how do you design a machine? B followed by B, then you go to final state. Okay. But now in this process, should never go to dead state. Why? If you go to dead, after the double B may come. You can't come to the final once you go to dead. That is the difficulty, right? So you should never think about dead state in this ending condition, right? Now our target is to stay here when you get double B. Now before this B, if A comes, will you wait or will you go to dead? You will wait. So I'll stay here any number of A's because I don't know when double B comes. So I stay here. After B, when A comes, don't go dead. I'll come back. I'll look for 2 consecutive B's because I need 2 consecutive B's at the end. When A comes, I'll come back. Right. If this B comes, don't assume your string is over, because after double B, you may have something you don't know, right? After double B, if B comes, you are safe. Why safe? Because double B followed by any number of B's, it's still ending with double B only. You see that? Once you get a double B, any number of B's are coming. Still it is ending with double B only. But after this double B or after this B, if A comes, then whole sequence is interrupted. Now again you have to look for double B. So you should come here to look for double B again. Is your machine over? Yes, see that. From this AB covered, from this AB covered, from this AB covered. Now any string which is ending with double B, you will always halt here. If not ending with double B, definitely you will halt here. That means whenever the string is halting here, it is invalid. Whenever the string halts here, it is valid, because this state represent ends with double B. Okay, how many states required? 3 states. 3 states, which is the right answer. Okay, so this kind of problems are really interesting, and in the GATE exam, ending with 2 consecutive B's, ending with 3 consecutive B's, or containing 3 consecutive A's, these questions are happened many times, and it may come again in the future. Okay, so I hope now onwards you can think about how to solve them. Like this problem is the third symbol from the beginning is B, because first 2 symbols are any, because you can see this is same as A plus B followed by A plus B followed by B followed by A plus B whole star. It means First two symbols, we don't care, anything could happen, but third has to be B. That means minimum string will definitely have 3 length, right? Third position is B. Straight away you design, you will get the answer. First position, I don't care, but somebody should come. And second position, anybody, that's fine. But third position has to be B. If not B, then go to dead. Go to dead. So that would be A and go to dead. The third symbol never be A, that's guaranteed. Once third symbol is B, we don't care because everything is accepted after that. What do you see in the expression? Same thing replicated on the machine, but only thing is when the third symbol is A, you should go to dead state, because every string in the sigma star will have exactly one path in the DFA, right? Whether string is accepted or not accepted, DFA will have exactly one path. That is the beauty of the DFA. It will show a path. It will hold somewhere in the machine. Okay. So how many states you have? You will have 5 states. The third symbol from the beginning is B will have 3 plus 2, 5 states. In case in the exam the same kind of question comes like this, nth symbol from LHS or from begin is B or A, doesn't matter. Begin is B. How many states you will take? Here third is there. So after 2 symbols, third symbol, you got total 3 plus 2. And here you will have n plus 2 in DFA. If it is NFA, this state will not be required. There you have n plus 1. We'll see later. But nth symbol from begin is B. In DFA, you will require n plus 2 states. Fine. Okay. Can you understand what is the meaning of this one? How many states in DFA for the given language? But what is the language? So look at the positions. The first is any, second is restricted. So second symbol is A, third is any, fourth symbol is B. So in the language, second symbol is A and fourth symbol is B. That's your condition. So it's very simple again. The first is any. Any means either A or B. Second symbol is A. If not A, then you must go to dead state. I'll show that. And third symbol is A or B. Fourth symbol must be B, otherwise go to dead. And after that, anything is fine. Now, you must remember this. When the second symbol is not A, that should be B, go to dead state. In this sequence, second symbol never be B, right? And third, fourth symbol never be A. So if not B, if not B, it will be A only. In case the fourth symbol is A, go to dead and say that the string is invalid after reading whole string. So any symbol is missing, AB, 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 and AB. So that should be guaranteed in DFA, should not miss even one transition while constructing. So we'll have 6 states. Again, none of this, but number of states will be 6. So some of the homework questions I am going to give you in DFA, please construct them, and in case if you have any doubts, please keep discussing below this video. I'll help you what is the right answer, how to approach it. Okay, so let me give you a lot of homework problems for you. This is starting with double A or double B. Definitely will have a dead state. Okay, if you get after A B or after B A, you should go to dead state. So this is a very interesting problem, and take it as homework. Minimum string is double A or double B, that you should design, and just find out how many states you will have, 4 or 5 or 6, whatever. And this problem ends with double A or double B. I already helped you, ends with double B. Now it's ends with double A or double B. You will not have the dead state here, but in the previous problem you may have you will have dead state for starting condition, but ending condition you will not have. Please take it as homework, and please discuss below this video. Okay, one of the beautiful question in the gate, which is, which of the following language can be recognized by a DFA? That means, who is having a DFA? And if you can understand the problem, then only you can tell which one will have a DFA to accept. Now look at the numbers 1, 2, 4, 8, 2 power n written in binary, means in terms of the sigma over 0, 1, right? So what is the meaning of this? How do you get this 1? 2 power 0. How do you get this 2? 2 power 1. How do you get this 4? 2 power 2. How do you get this 8? 2 power 3, and so on. These numbers you wanted, but that should be written in binary. How do you write this 2 power 0? 1, 1, right? You know that, right? 2 power 0, 2 power 1, binary number. How do you represent? This is only one way, right? If I keep this 1 and remaining all zeros, which is equal to 2 power 0. If I keep this 1 remaining all are 0, this is equal to 2 power 1. Or 2 you can say, right? This is equal to 1, this is equal to 2. And if I keep this 1, what does that means? It's equal to 2 square, which is equal to 4. And similarly 1 remaining all are 0, which is equal to 2 power 3, nothing but 8. So now this is your binary strings. These are your binary strings. And if you are writing in binary, can you form an expression for this? Can you see that? The one in entire sequence in the string will have only 1, 1. That means for this, you have a 1 before after any number of zeros. Is it regular expression or not? Yes, you will have a DFA for this, no doubt, because I have written regular expression for it. Right? This number will definitely give you these numbers when you convert into decimal of the binary. So when you convert them into binary, this is your binary string. It will definitely represent one of this 2 power form. Okay, so any one of this digit, only one of this, if you keep 1, you will have this 2 power form, because your binary number is formed based on this 2 power sequence. Okay, that is the reason the A will have a DFA. It was an MCQ question. The first option itself you got an answer, so blindly you can choose it, but you should know what are other things too. Anyhow, in the coming topic, finding regulars, non-regulars, I'll come up with this too, but I'll explain now. The numbers which are written in unary. Unary means, let's take symbol A. So A power 2 power n. And if the language is A power 2 power n, where n is greater than or equal to 0, it will not form arithmetic progression. I will be discussing this because right now our knowledge is not enough to say non-regular. I told you we are learning regulars, but non-regulars will take time. As you know, you should know a lot of regular languages and you should know property of non-regulars too. So this one, it is over one symbol, will not form arithmetic progression because 2 power n, which will not give you any cycle when you design DFA. So this is going to be non-regular. I'll show you this later on, which languages are non-regular later on, right? So you can represent this second problem as A is one symbol, sigma over, written in unary means one symbol. That is one symbol I have taken A, or you can take 0 or you can take 1, doesn't matter. But symbol A power 2 power n, there is non-regular language. And the set of binary strings in which the number of zeros is same as the number of ones are really that is W, such that W belongs to 0, 1 whole star, where number of zeros is equal to number of ones. And obviously there is a dependency which is also non-regular. And look at this, you have a 1 here, okay, 1 here, and double 1, double 1. There is a dependency again. Except the first string, you see that the language 1, the first one I have taken 1 separately, remaining all you see union, there is a 0, and before and after the 1 power is same. Yes or no? And when you look at this, of course the n has to be greater than or equal to 1. N has to be greater than or equal to 1. It's not 0, right? So 1 0 1, double 1 0 double 1, triple 1 0 double 1. So before 0, after 0, same number of ones. That dependency is not possible with the DFA. If you have like this, 1 star 0 1 star, that's okay, you can do it. But 1 power n 0 1 power n, how do I remember before 0, after 0, same number of ones? If you don't have any same, then I can put a self loop before 0, after 0 I can put a self loop for 1, it will work. But you can't keep self loop because you have a dependency. So the last 3 problems you can't have a DFA, and which is really important question. But I hope this question and this question will be covered again in non-regulars. So there we will practice why these are non-regular again. But right now your knowledge is important, why this is regular or why this is having DFA, because we can design a DFA for this. Can you design DFA for this? Yes or no? So let's try this. DFA 0 star 1 0 star, minimum string is 1. What do you do? Before 1 any number of zeros, after 1 any number of zeros. Clear? After this second one never comes, so you go to dead. That's enough. Over. If you design this DFA, that will accept all the binary strings which are equivalent to this numbers only. Okay. So with this we have understood regular expressions and DFA. And what else is missing here is non-deterministic finite automata, and some other important points will be covered in another video. But main focus is like I have focused on main important topics of DFA and regular expression, and definitely I'll be covering in end of this first topic, regular languages. You will be seeing non-deterministic finite automata just to understand how easily you can design. Okay, so let's see you in the next video with other topic, regulars and non-regulars. So before concluding today's lecture, let me explain what we have done so far. In this video, we have learned the basics like strings, languages, and basic things like Chomsky hierarchy. That would be fine. And after that, we have started with regular expressions. We have learned the 4 operators like or, concatenation, that's a dot, and then Kleene star, and then Kleene plus, 2 unary and 2 binary. And then we have mostly focused on DFA to accept the languages. Okay, and here these 2 models, or these 2 helps us to represent regular language. Apart from this, you have other models like NFA, regular grammars, okay, which are also going to represent regular languages. So in future we will be learning, after knowing about regulars and non-regulars, I'll quickly finish the NFA and regular grammar along with regular language and non-regular languages. Okay, let's see you in the next video with another topic, which is regular languages and non-regular languages. Really, if you like this lecture, please let me know, and I appreciate for your valuable feedback, and please keep asking your doubts, and I'm happy to help if you have any comments related to this lecture. Thank you so much. Bye bye. Take care.